Cakes, muffins, and apple pies are crafted through a precise blend of technique, timing, and tradition. From mixing silky batters to shaping delicate crumb structures to filling crusts with slow-stewed apples, every step transforms simple ingredients into iconic baked classics. Today, we reveal the controlled processes, specialized tools, and quiet innovations that bring these pastries from raw components to finished treats fresh from the oven. In the high-speed world of industrial cake manufacturing, the transformation from raw material to finished product begins with movement, controlled, constant, and calculated. Deep inside the mixing hall, massive stainless steel bowls, each one the size of a small car, rotate slowly at first, their blades turning with deliberate resistance. This isn't simply stirring. The mixers are carefully calibrated to develop structure, to whip precise amounts of air into the batter, to emulsify, to fold, and to unify a mixture that must be strong enough to rise, but light enough to remain soft. As the first phase begins, pumps activate in rhythm, drawing liquid components through heat-regulated pipes, while dry materials enter the system through sealed conveyor tubes, dropping with a muted rush into the vortex of motion below. The mixing is governed not by time alone, but by sensors measuring viscosity, torque, and aeration. As the blades accelerate, the machine monitors every variable in real time. Too much speed, and the batter overdevelops, becoming tough and elastic. Too little, and it stays uneven, heavy, prone to collapse during baking. When the internal diagnostics hit the target range, the machine stops. Then, a massive hatch swings open underneath the bowl, and the batter flows, not in a trickle, but in a steady, smooth sheet, down into the waiting hopper tanks below. These hoppers don't just store, they agitate, maintain temperature, and meter out batter to the depositor line. The transition from mixing to depositing is seamless. Conveyor belts carry empty cake trays into position beneath a row of pneumatic nozzles. As the trays align, the nozzles descend, and with one swift, synchronized pulse, exact quantities of batter are released. Each cavity fills with the same volume every time, no variation. The depositor can switch between multiple product formats on demand, adjusting fill volumes, patterns, and nozzle heights through pre-programmed settings, allowing the line to shift between single-serve snack cakes, multi-layer sponge rounds, or filled loaf cakes without stopping production. For cakes with layers or inclusions, the system operates in stacked phases. The first layer of batter is dropped, the tray advances, and then a secondary depositor releases a ribbon of fruit puree, chocolate, cream, or other fillings. The tray continues forward, and the final layer of batter is placed on top, encapsulating the filling in the center. Everything happens in motion, with no pause between steps, and no human hands involved. Each action is controlled by sensors and servos, responding in milliseconds to maintain absolute consistency. From depositing, the trays move directly into the baking tunnel. This isn't a conventional oven, but a controlled thermal corridor divided into zones, each one gradually increasing or decreasing in temperature depending on the recipe's profile. As the pans enter, the initial zone introduces a dry, preheated airstream that begins to activate the leavening agents within the batter, causing rapid but controlled expansion. In the middle zones, the cakes firm up, their internal temperature climbing steadily toward the final set point. Here, sugars begin to brown, moisture begins to migrate toward the edges, and the tops dome slightly before settling into their final shape. Toward the end of the tunnel, the heat is dialed back, allowing the outer crust to stabilize without cracking and giving the cakes their familiar golden finish. Every part of the oven is monitored. Temperature, humidity, airflow velocity, all logged in real time. Infrared sensors scan the surface of the cakes as they pass, measuring browning and structure. The belt never stops. Cakes move from raw to baked in under 10 minutes, depending on size. And by the time they exit the final zone, the core has reached the precise temperature needed for a perfect set, while still being soft and resilient to touch. They leave the oven hot, over 90 degrees at the center, and far too delicate for handling. So the pans are routed directly into the spiral cooling tower. This massive vertical system lifts the trays upward on a continuous belt, winding them slowly through a tall, temperature-controlled chamber where cool, filtered air circulates from all directions. The spiral design allows time and space to cool gently, without forced shocks that could cause cracks or shrinkage. Over the next 20 minutes, the cakes release steam from the inside out, stabilizing their shape, color, and crumb texture. When they reach the base of the spiral, the pans tilt gently, and the cakes are lifted out, using vacuum heads mounted to robotic arms. These heads apply just enough force to lift without distortion, and release each cake onto a new conveyor belt, lined with soft rollers that minimize pressure points. The empty pans are cleaned automatically and sent back to the front of the line on an overhead return track. There's no pause in this cycle. As cakes exit the oven, new pans are already filling at the front. Depending on the product, the next stage may involve slicing. Ultrasonic blades, oscillating at extremely high frequencies, glide through each cake with no friction and no crumbs. These blades never tear or compress. Whether cutting large sheet cakes into precise rectangles or splitting sponge rounds into layers, the system delivers uniform cuts across every dimension, synchronized to the belt speed and guided by real-time vision alignment. For layered cakes, a filling line follows. Cakes move beneath depositor heads that lay down cream, mousse, ganache, or fruit fillings in thick, even waves. The second layer is placed by a robotic arm that aligns it using pressure sensors to ensure it lands cleanly, sealing the filling between layers with no offset or shift. Excess is trimmed automatically. If the cakes are enrobed, they pass into a coating tunnel. In this section, a waterfall curtain of melted chocolate, icing, or glaze pours continuously from a wide spout, enveloping each cake as it moves through. Below the belt, a catchment basin collects runoff and recirculates it. Air knives follow immediately after, blowing off any excess coating to ensure a smooth, even finish. Sensors track coating thickness, and heaters maintain the fluid temperature within a tight range to ensure shine and flow remain stable throughout the batch. While the coating is still warm, toppings are applied. These may include nuts, sprinkles, sugar crystals, or textured crumbs, dispensed through vibration-fed shakers positioned above the belt. The timing is exact. Toppings must hit the surface before the coating sets, and they must stick without sliding. If a pattern is required, a robotic arm equipped with targeted nozzles delivers specific designs, alternating colors or writing directly onto the icing in pre-programmed scripts. Wrapped cakes move onward to the flow wrapping station. Each cake is aligned on the belt by guide rails, passed beneath a scanner that checks for position, then enveloped in pre-printed film that wraps from below. Heated jaws seal the seams on the underside, and at both ends in one smooth motion. For larger cakes or family-sized products, a form-fill seal machine places the cake into a clear tray and heat shrinks a film tightly over the top. Label applicators add branding, barcodes, batch numbers, and expiration dates using thermal inkjets or direct print heads. From wrapping, the cakes move to inspection. A battery of high-speed cameras mounted above and to the sides of the belt analyze every product for shape, size, color, print alignment, and wrapping quality. The system can detect a deviation as small as a few millimeters. Any flawed cake, too short, too dark, incorrectly wrapped, is flagged and removed by a pneumatic pusher into a rejection lane. The rest continue on. Packing is fully automated. Robotic arms equipped with vacuum grippers lift wrapped cakes and place them into boxes in predetermined configurations, single rows, stacked layers, or nested shapes. Cartons fold automatically, are glued shut with hot melt adhesive, and receive their own set of labels and date codes. Palletizing robots stack the boxes with precision, inserting slip sheets between layers to stabilize the load. Once complete, each pallet is stretch wrapped and labeled for shipment, then transferred by automated guided vehicle to cold storage or dispatch. Muffin production inside a factory isn't just scaled up baking, it's a continuous, highly synchronized system of motion, timing, and precision engineering where hundreds of muffins are created every minute and where not a single one is left to chance. It starts long before a single tray sees batter, deep in the heart of the production floor, where massive stainless steel mixers stand ready, surrounded by automated hoppers, dosing lines, and temperature-controlled ingredient feeds that keep everything flowing with mechanical consistency. Inside the first mixing vessel, the transformation begins. The bowl is loaded automatically, not by hand, but by metered pumps and augers, delivering exact amounts of wet and dry ingredients through enclosed transfer lines. The mixer blades start slow, rotating through thickening liquid, folding and drawing dry powder into the vortex. As the mixture thickens, the paddles accelerate. These aren't random speeds. Each gear, each change in direction is pre-programmed to hit target aeration levels, to build structure into the batter without overworking it. In muffin production, texture is everything, and these machines are calibrated down to the decimal to make sure the batter holds air without collapsing later in the oven. Real-time sensors monitor every metric: viscosity, torque load, internal temperature. Nothing moves forward until everything is exactly within specification. When the batter is ready, the bottom hatch of the mixer opens hydraulically and the batter flows down through a pipe, thick and glossy, into a holding tank below. Inside that tank, slow-moving paddles keep the mix from settling. There's no foaming, no separation, and the temperature is held perfectly stable. From this point on, everything moves in rhythm. The batter tank connects directly to a row of depositors mounted over a fast-moving conveyor line that carries endless rows of muffin trays. As each tray arrives beneath the filling heads, a set of precision nozzles drops down, positions itself just above each cavity, and releases a carefully measured pulse of batter. Each deposit is fast and clean, with a sharp cutoff at the end to prevent dripping. The volume is exact, tray after tray, cavity after cavity, row after row. If inclusions like blueberries, chocolate chips, or nuts are part of the product, those are added in line. A separate feeder system sprinkles them evenly into the batter stream just before depositing. The nozzles pulse, the belt moves, and the process repeats, non-stop. If the muffins are swirled with fruit puree or topped with crumble, those steps follow immediately. A second head deposits a ribbon of fruit on the surface, and rotary brushes spin in carefully tuned patterns to drag it through the top layer in clean, consistent swirls. Crumble or sugar toppings fall through vibrating screens, shaking down onto the tops with a light, even coverage before the tray rolls forward toward the oven. The baking system isn't a conventional oven. It's a tunnel, a long, temperature-zoned corridor stretching across the length of the facility. Muffin trays enter on one end and move slowly through each zone, exposed to controlled bursts of hot air from above and below. The airspeed, heat intensity, and humidity change gradually as the trays progress. The first zone triggers the leavening reaction. The batter puffs, lifts, and begins to dome. In the next zone, the structure sets. Moisture is driven out slowly, and the exterior forms a soft, golden crust. The final zone dries the base and stabilizes the crumb. At all times, thermal cameras scan the surface of the muffins. Sensors embedded in the conveyor read temperature profiles from below. If even a single muffin appears overbaked or underdeveloped, the belt speed adjusts. If the top crust browns too fast, airflow redirects. The system is fully closed loop, meaning it makes micro adjustments constantly without stopping the line. When the trays exit the oven, the muffins are hot, above 95 degrees Celsius inside, and completely fragile. They can't be touched, moved, or packaged until they've cooled. So they move into the spiral tower, a massive, multi-level cooling system that gently carries trays upward in a slow-moving helix. Fans push filtered, cooled air through each level, and over the course of 20 minutes, the muffins descend in temperature, firm up structurally, and stabilize in moisture content. The tops remain soft, but dry. The crumb finishes setting. The aroma of baking lingers through the air vents long after the muffins leave the spiral. When they emerge at the base, they're ready for the next step, depanning. A high-speed robotic system equipped with vacuum suction heads drops down, locks onto each muffin from above, and lifts it cleanly out of the tray. There's no squeezing, no bruising, and no scraping involved. The muffins are placed gently onto a transfer belt that moves them forward toward the wrapping area, while the now empty trays head toward the automatic pan washer and loop back to the front of the line. Wrapped muffins start with alignment. Guide rails space, each one precisely before they enter the horizontal flow wrapper. Pre-printed film unwinds from massive spools, meets the conveyor, and forms a tube around the muffin. Heat-sealing jaws clamp the edges shut on the bottom, while crimping heads close the front and back. The film is sealed in less than a second per unit. For multi-packs, muffins are grouped upstream by a timing screw that arranges them in rows before entering a larger wrapper or carton. Every wrapped muffin then passes under inspection. Optical scanners check for seal integrity, print accuracy, and product position. Anything that's off-center, underweight, or miswrapped is rejected instantly by a pneumatic pusher. Accepted muffins continue on to final packing, where robotic pick-and-place arms load them into cartons, clamshells, or trays. Carton erectors fold and glue boxes on demand. Labels print batch codes, barcodes, and expiration dates live. Palletizers stack the finished cases in tight formations, applying stretch wrap with a rotating arm that binds the load into a single, stable unit ready for shipping. Behind the scenes, a central control system connects every station. The mixers, ovens, depositors, wrappers, slicers, conveyors, all are plugged into a real-time production network that monitors flow rate, uptime, errors, yield, and diagnostics across the line. If the batter thickens beyond tolerance, the depositor pressure adjusts. If the oven lags a few degrees behind target, the belt slows by a fraction of a second. The system learns from previous batches, adapting recipe parameters to current humidity levels or ingredient characteristics. It doesn't just run, it optimizes continuously. Clean-in-place systems activate between batches. Mixing tanks flush with hot water and sanitizing solution. Batter lines are drained and purged with compressed air, then rinsed again. Depositor heads are dismantled by robotic arms and pass through a pressurized wash tunnel. Ovens cycle down and go through a heat sterilization protocol. Cooling towers are vacuumed, air filters replaced, and conveyor belts wiped and scrubbed. Nothing rests. Every part of this process exists to serve one goal: total consistency at high speed. From the moment a batch begins mixing to the final pallet rolling out of the warehouse, each muffin is shaped by a continuous current of controlled motion. There's no downtime. There's no guesswork. Every curve in the top, every moist crumb in the center, every sealed wrapper is the result of tightly timed heat, weight, air, and movement. The manufacturing of apple pies at factory scale is a seamless chain of automation and mechanical precision where every motion, from dough forming to fruit filling, from baking to boxing, is timed down to the second, measured in grams, and repeated thousands of times per hour without deviation. The process begins at the core, with the dough. In the dough room, massive mixers begin to rotate. their stainless steel paddles submerged in an evolving mass of flour, fat, and water. The blending is slow at first, a measured rotation that folds dry into wet, gradually forming a heavy, pliable dough. As the structure develops, the blades speed up, kneading the mass just enough to form elasticity without overworking it. Inside the bowl, torque sensors monitor resistance, and temperature probes measure the internal heat generated by friction. The dough is not simply mixed, it's tuned, calibrated for stretch, softness, and handling. Once the target consistency is reached, a bottom hatch releases the dough into a waiting hopper. This hopper feeds the dough into a sheeting system, where a series of large, motor-driven rollers press it flat. The sheet passes through progressively narrower gaps, each stage compressing it thinner, smoother, and more uniform than the last. By the time it exits the final roller, the dough is a wide, continuous ribbon of consistent thickness, cool to the touch, with no cracks or tears. Guillotine blades cut the sheet into manageable strips, which are immediately fed into a pie-forming module. Each strip is aligned and dropped into a rotary press that forms the bottom crust. Molds shaped like pie tins circle a large carousel, where robotic arms drape each dough circle into place. Another mechanism presses the dough gently into the mold, shaping the base while trimming excess at the edges with a rolling blade. The result is a perfectly shaped shell, firm enough to hold its form, but soft enough to bake evenly. As the dough bases are formed, another section of the factory is already working in parallel, preparing the filling. Pre-cooked apple slices, cooled and stabilized, move through a chute and into a horizontal conveyor system that gently shakes and spreads them out. The apple pieces are firm but tender, glossy with syrup, and coated to prevent clumping. These slices are then portioned by weight, fed into rotary depositors that drop exact amounts into the formed dough shells below. Every pie gets the same number of slices, arranged naturally by gravity and spacing. The syrup, thickened and warm, is pumped through heated lines to remain fluid. It arrives at a nozzle bank positioned just above the filling line, and as each pie advances under the nozzles, a pulse of syrup coats the apples. The timing is so precise that there's no overflow, no waste, just a clean layer that locks in moisture and flavor. As the filling settles, the pies move forward on the line. Now comes the top crust. Depending on the variety, this may be a solid sheet, a lattice, or a crumble topping. For covered pies, a second dough sheet, cut from the same roller system, is dropped onto the filled bases by a vacuum placer. The crust is sealed to the base with a crimping wheel that spins along the edge of the mold, pressing the layers together and forming a decorative ridge. For lattice pies, strips of dough are woven by a mechanical loom, layered onto the pies by a robotic arm, and sealed with light pressure. Crumble toppings are dispensed from overhead, falling in a soft shower from vibrating feeders that shake just enough to distribute the topping evenly without crushing the apple pieces below. Once topped, each pie passes beneath a scoring unit. Small blades descend to cut vents in the crust, uniform slits that allow steam to escape during baking. Then, a fine mist of glaze or egg wash is sprayed across the surface by nozzles that fan back and forth in fluid sweeps, giving the crust a glossy, golden finish once baked. Sugar crystals or coarse toppings are applied immediately after, sticking to the glaze before it sets. The pies then move toward the oven, traveling in trays that roll onto a wide, continuously moving mesh belt. The oven itself is a massive tunnel, segmented into zones of rising temperature. As pies enter the first zone, the dough begins to puff and set. The crust firms at the edges while steam builds inside. Through the middle section, radiant heat drives moisture from the apples and syrup, reducing the filling to a rich, sticky consistency. The smell intensifies and the top crust begins to turn golden. In the final zone, the heat drops slightly, allowing the pie to finish baking without drying out. Internal probes track the core temperature of random pies, and the belt speed adjusts if the readings fall outside the tolerance range. By the time they exit the oven, the pies are fully set, crust golden and flaky, filling bubbling gently beneath, the surface glistening. But they're still too hot for handling, so they move directly into a spiral cooler. This towering system lifts the pies upward on a long, coiled belt, passing them through layers of circulating ambient air. Fans push filtered air across the surface in precise crossflow, cooling the pies from the top down and the inside out. Over 20 minutes, the pies descend the spiral, their internal temperature falling gradually to a stable level, locking in structure and preventing condensation. Once cooled, the pies enter the depanning system. Vacuum lifts grip the crust gently, raising each pie from its mold without cracking the edge or disturbing the topping. The empty pans are immediately cleaned by a dedicated washer and sent back to the forming station, while the pies continue forward. If the pie is to be sold whole, it proceeds straight to wrapping. If it's to be sliced, it moves to the ultrasonic cutter. This cutter is no ordinary blade. It vibrates at extremely high frequency, slicing through the delicate crust and dense filling with no drag, no crumbs, and no displacement. Each pie is cut into exact portions, the edges clean and defined. The system aligns each slice for individual wrapping or trays them together for multi-packs. Visual inspection cameras check for completeness, cut accuracy, and surface appearance, rejecting any pies that show separation, overbrowning, or deformity. At the packaging station, the pies move toward wrapping tunnels. For whole pies, clear plastic domes or shrink-wrapped trays are applied using form and seal machines. For slices, flow wrappers enclose each portion in printed film. All products are labeled automatically. Production time, lot number, expiration date, all applied in motion by thermal inkjet or laser systems. Optical sensors verify the print before the pie continues. Packed pies are grouped and placed into cartons by robotic arms. Cartons are erected, filled, sealed, and stacked with minimal human oversight. At the end of the line, palletizers lift and arrange boxes onto wooden platforms, interleaving each layer with slip sheets for stability. The entire stack is shrink-wrapped and labeled before being routed to dispatch. Throughout the process, the line doesn't stop. Not for filling, not for slicing, not for packaging. Each section is tied to the next through real-time communication. If the oven slows, the depositors slow. If the cooling spiral reaches capacity, the forming line is paused until space clears. The factory operates as one living system, constantly adjusting to ensure flow stays balanced and product integrity never wavers. At full operation, the line produces thousands of apple pies per hour, every one shaped, filled, baked, cooled, and boxed without ever being touched by a person. Everything is guided by servo motors, cameras, temperature probes, and air pressure. No guesswork, no variation. Each pie is exactly as the one before it. Same dome, same color, same weight, same slice. Wheat flour is first delivered into large stainless steel silos where it is aerated and sifted to remove any foreigns, raise the pH of the dough, and produce the distinctive yellow color and firm, springy texture characteristic of cup noodles. The mixing chamber is equipped with twin shafts fitted with spiral paddles. These rotate in opposite directions, kneading the flour and water into a coarse dough. After a preset mixing time, the dough exits through a discharge chute and drops onto a sheeting conveyor. A pair of compression rollers press the dough into a wide, flat sheet of uniform thickness. The dough sheet then moves through a series of calibrated rolling stations. Each set of rollers reduces the thickness incrementally. Final gauge rollers press the sheet to a precise thickness, usually around 1 mm, before it enters the slitting unit. Here, rotary cutting wheels slice the sheet into long continuous strands. The blades rotate in exact synchrony with the moving dough, ensuring even noodle width and preventing tearing or overlap. The cut strands are separated by a vibrating spreader and immediately fed into a wave former. This mechanism applies a rhythmic up and down motion as the noodles pass over metal rods. The result is the iconic wavy noodle shape. The wave pattern is fixed into the strands by partially steaming them immediately after shaping. The noodles then enter a vertical steam chamber. Superheated steam, delivered through multiple nozzles, cooks the noodles for a brief but precise interval. The starches gelatinize and the surface becomes slightly sticky. This step fixes the texture while keeping the strands pliable. Upon exiting the steam chamber, the noodles are portioned. A wire cutter slices the strands into fixed lengths, which are gathered into bundles by rotary collectors. Each bundle is compressed slightly to form a compact cake. These cakes are positioned over pre-formed polystyrene foam cups on a conveyor system. Using a synchronized pick-and-place system, the noodle cakes are inserted into the cups from above. The cups themselves are formed earlier in the process using vacuum thermoforming machines. Polystyrene sheets are heated and drawn into mold cavities using vacuum suction. After forming, the cups are trimmed, stacked, and fed automatically to the noodle filling station. Once the noodle cake is placed into the cup, it proceeds to the dehydration stage. Unlike many instant noodles that are fried flat, cup noodles use a unique upside-down flash frying method. The filled cups are inverted and loaded onto a wire mesh conveyor belt that carries them through a continuous oil fryer. The oil, typically palm oil or a blend of vegetable oils, is maintained at a stable high temperature, usually between 140 degrees Celsius and 160 degrees Celsius. As the cups travel upside down through the fryer, the noodles are rapidly fried. Moisture evaporates from the strands, creating a porous, dehydrated structure that can be rehydrated quickly with hot water. The upside-down orientation ensures that the noodle cake maintains its shape and settles evenly inside the cup. Frying time is tightly controlled to prevent overcooking or excessive oil absorption. After frying, a separate filling system dispenses dried soup base and dehydrated vegetables or meats into each cup. The powder and inclusions, such as corn, peas, green onion, shrimp, or meat bits, are pre-blended in large hoppers. These are vibrated to prevent clumping and ensure free flow. As each cup passes underneath a dosing unit, precise quantities of the flavor mix and inclusions are released. Auger fillers handle the powder, while rotary cups or belt feeders portion the solid pieces. Lidding is the next step. A continuous roll of pre-printed aluminum foil is fed through a cutting die and sealing station. The foil is heat sealed onto the lip of each cup using a combination of pressure and temperature. The seal must be strong enough to prevent contamination, but easy to peel by hand. A vacuum system removes any air trapped between the noodle surface and the foil lid prior to sealing, reducing oxygen exposure and extending shelf life. Lidded cups proceed to the shrink sleeve labeling unit. A plastic film sleeve is positioned over each cup and then passed through a steam tunnel. The heat causes the sleeve to contract tightly around the cup, conforming to its shape. This sleeve contains branding, nutritional information, and preparation instructions. The orientation is adjusted using optical sensors to ensure perfect alignment with the cup's front face. After labeling, the cups are inkjet coated with production data, including date codes and batch numbers. A vision inspection system verifies code legibility and checks for misaligned labels or incomplete seals. Any defective cups are rejected automatically onto a side conveyor for rework or disposal. The finished, sealed, and labeled cups then enter the secondary packaging area. Depending on the distribution format, cups are grouped into packs of 6, 12, or 24 using a mechanical collator. These are pushed into pre-erected cardboard cartons supplied by a case-forming machine. Hot melt adhesive is applied to the flaps using spray nozzles, and the boxes are pressed shut by compression rollers. Each sealed carton passes over a check cameras scan the labels to verify pre-filtered and UV sterilized before use. Oil for frying is circulated through a closed-loop filtration system that removes particulates and maintains clarity. Spent oil is drained and replaced after a set number of frying cycles, tracked by production batch logs. Quality control checkpoints exist at every stage. During dough mixing, operators monitor water absorption and dough elasticity using resistance sensors and torque readings. Sheet thickness is verified with laser micrometers before slitting. The width and wave depth of the cut noodles are measured optically in real time. Caramelization level and texture of the fried noodles are sampled from each batch and tested for rehydration time and oil content. Soup base and seasoning powders are blended in large ribbon mixers fitted with load cells and sampling ports. Moisture levels in dried inclusions are measured by infrared sensors before dosing. Sealing strength of foil lids is tested by applying standardized pressure until rupture. Seal failures beyond tolerance trigger immediate alarms. The entire production process is managed through a distributed control system, DCS. Each major component, mixers, fryers, fillers, lid sealers, labelers, is equipped with a PLC. These units communicate with a central control interface where operators can monitor flow rates, dough temperature, oil usage, fill weights, and output speed. Recipes and production profiles are saved digitally, allowing fast switchover between flavor variants or cup sizes. Sanitation is performed on a rotating schedule. Between shifts or recipe changes, dough mixers and noodle rollers are cleaned with high-pressure water and food-safe detergents. Fryers are drained and flushed with flushing agents. Dosing systems for powders and inclusions are disassembled and brushed manually. Cup molds and conveyors are wiped down using alcohol-based surface cleaners. Durum wheat semolina is the primary raw material used in pasta manufacturing. It arrives in bulk and is unloaded into stainless steel silos equipped with aerators and sifters. These silos store the semolina under controlled temperature and humidity. From the silos, semolina is conveyed pneumatically into a weigh hopper, where precise quantities are measured before entering the mixing system. Water is added to the semolina through a dosing pump as both ingredients enter the horizontal pre-mixer. The water is filtered and temperature controlled to ensure consistent dough development. The pre-mixer is a twin-shaft system with overlapping paddles that combine the semolina and water into a crumbly, granular dough. This stage typically lasts for 10 to 15 minutes, and no gluten is developed here, only hydration. The hydrated mixture then flows into a vacuum kneading chamber. This vessel contains a large screw auger that compresses and kneads the dough under vacuum. Air is evacuated to eliminate oxidation and reduce bubbles in the final product. Under pressure, the dough begins to form a cohesive, elastic mass. The kneading screw pushes the dough forward into the pasta press. The pasta press consists of a compression screw housed in a barrel. As the screw rotates, it applies mechanical pressure, forcing the dough forward toward the die head. Just before extrusion, the dough passes through a second vacuum chamber that removes residual air. This double vacuum system ensures smooth surface texture and prevents breakage during drying. The die head holds a brass or Teflon-coated die plate with dozens of holes shaped according to the type of pasta being produced: spaghetti, penne, fusilli, farfalle, or others. As the dough is pushed through the die, it takes on the corresponding shape. For shortcut pasta, like penne or rigatoni, a rotating blade mounted just beneath the die slices the extruded strands at uniform lengths. Blade speed and position are adjustable to control piece size. Immediately after cutting, the pasta falls onto a vibrating belt that separates and aligns the pieces. The belt feeds into a pre-dryer, a short chamber with warm air at low humidity. Here, the surface moisture is reduced to prevent sticking and deformation during handling. This stage lasts only a few minutes, but it's crucial for shape retention. For long-cut pasta, like spaghetti or fettuccine, strands are laid continuously onto rods or loops by an automated looping device. These rods are transported by conveyor into multi-stage dryers. The entire drying process is tightly regulated. Primary drying begins in a chamber where temperature and relative humidity are gradually increased. Warm air, typically between 55 degrees Celsius and 75 degrees Celsius, circulates through the pasta via fans and ducting systems. The airflow direction alternates to ensure even drying. Sensors monitor surface moisture content, and the pasta's structure begins to stabilize. In the next phase, stabilization, the temperature is held steady while humidity is slowly reduced. This allows the interior of the pasta to release moisture at the same rate the surface loses it, preventing cracks and internal stress. Each dry zone has PID controllers that adjust heat and airflow in response to real-time sensor feedback. The final phase, cooling, brings the pasta down to ambient temperature using filtered, dehumidified air. For long pasta, the hanging rods pass through these zones slowly over 6 to 10 hours. Shortcut pasta is dried on vibrating trays or mesh belts in large cabinet dryers that rotate trays periodically for even exposure. After drying, long pasta is automatically lifted from the rods and cut to standard retail lengths, usually 25 centimeters. The cut strands fall gently onto conveyor belts equipped with brushes that remove excess flour and broken tips. The pasta is then transferred to a vibrating sifter that separates any fines or small fragments. Short pasta, once dried and cooled, is conveyed into a series of screens and classifiers. Pieces outside the tolerance range, too short, broken, or malformed, are diverted to rework bins. Accepted product moves on to weighing and packaging. For packaging, pasta is first collected into hoppers above a multi-head weigher. These weighers use load cells and sensors to release exact quantities, 250 g, 500 g, or 1 kilogram, into form fill seal machines. Plastic film from large rolls is drawn into a forming collar and sealed around the falling pasta. Vertical sealing bars close the side, while horizontal sealing jaws crimp and cut the top and bottom. During sealing, vacuum nozzles or nitrogen flushing may be used to displace ambient air, extending shelf life. As each bag is formed and sealed, it passes beneath an inkjet printer that applies batch codes and expiration dates. Optical readers verify that print is clear and correctly positioned. For pasta sold in boxes, a different system is used. A volumetric filler dispenses pasta into an open-top carton traveling on a belt. Flaps are folded and glued by rotating arms, and the filled cartons pass through compression belts to ensure a tight seal. All packages, regardless of format, are collected into groups using collators. They are placed into corrugated cases by robotic case packers. Each case is built automatically from flat blanks sealed with hot melt glue and labeled using a print and apply labeler. Barcode scanners verify case content before palletizing. At the palletizing station, articulated robotic arms use vacuum grippers to pick and stack cases onto wooden pallets. Patterns are adjusted depending on case size and weight. Slip sheets may be inserted between layers for added stability. Once a pallet reaches full height, it is wrapped in stretch film using a turntable or robotic arm wrapper. The wrapped pallets are labeled and scanned into the warehouse inventory system. Forklifts or automated guided vehicles, AGVs, move the pallets to staging areas for outbound shipping. Throughout the process, quality control systems operate continuously. Semolina is analyzed for protein content, granule size, and moisture before use. Dough hydration is monitored using inline sensors that measure torque and consistency during mixing. Pasta diameter, wall thickness, and length are checked by laser micrometers at multiple stages. Moisture content in finished pasta is tested using infrared drying units or moisture balancers. Samples are also tested for cooking time, firmness, and swelling index. If any deviation occurs, the batch is flagged and removed from production. Clean in place, CIP, systems clean the dough mixers, extruders, and piping between production runs. Dry areas, like dryers and sifters, are cleaned manually using compressed air, brushes, and vacuum systems. Hygiene protocols are rigid to prevent contamination between product types. Die plates are removed and cleaned with pressurized water and ultrasonic tanks. Every die is catalogued and rotated based on shape and wear rate. Teflon-coated dies produce smoother pasta surfaces, while bronze dyes give a rougher texture preferred for sauce adhesion. Air used in drying and cooling is filtered and conditioned. HEPA filters remove particulates, while dehumidifiers ensure consistent airflow. Each dry zone is mapped for temperature and humidity uniformity, using multiple sensors connected to a centralized control system. The entire production line is governed by a SCADA, supervisory control and data acquisition system. Operators monitor flow, pressure, motor speed, and temperature in real time from touchscreen panels. Recipes for each pasta shape are stored digitally and recalled instantly during changeovers. Mechanical actuators adjust die plates, blade positions, and packaging formats based on the selected recipe. Ingredient handling is fully automated. Semolina flows from silos through sealed conveyors. Water is filtered, dosed, and monitored with UV sterilizers and flow meters. Lubricants used in machines are food grade and monitored to prevent cross-contamination. Production runs are planned in batches, but the process is continuous. Pasta moves through mixing, extrusion, drying, and packaging without interruption. Only during scheduled maintenance or product changeovers does the line stop. From flour to fork, pasta manufacturing is a highly engineered sequence of mechanical, thermal, and pneumatic operations. Dough becomes structured through pressure and hydration. Shapes are formed under vacuum and cut by precision blades. Moisture is drawn out gradually in chambers humming with air currents. Machines fill, seal, stack, and wrap, synchronized by sensors and driven by control logic. Macaroni and cheese manufacturing begins with the continuous production of elbow macaroni, the signature pasta shape. Durum wheat semolina is stored in sealed silos where it's kept under controlled humidity and aeration. The semolina is pneumatically conveyed to a weigh hopper, then released into a high-speed horizontal pre-mixer. As the mixer runs, filtered water is injected in precise amounts through a flow-controlled nozzle system. The mixture forms a coarse, granular dough with no gluten development at this stage. The moistened dough transfers to a vacuum kneading chamber. Here, a slow-turning screw applies pressure to compress the particles into a cohesive mass. A vacuum pump removes excess air, preventing oxidation and ensuring the pasta will have a smooth surface and uniform color. The dough advances through a compression auger toward the pasta press. At the end of the press, the dough passes through a forming die. For elbow macaroni, the die includes a curved extrusion channel that forces the dough into a bent tubular shape. As the pasta is pushed through, a rotating knife cuts the curved tubes at uniform intervals. Blade speed is adjusted in coordination with dough pressure to maintain consistent piece length, typically around 2.5 to 3 centimeters. Freshly extruded macaroni is fragile and contains residual moisture. It is transferred by vibrating conveyor into a pre-dryer. This chamber uses warm, low humidity air to gently reduce the surface moisture and fix the shape. This step lasts 1 to 3 minutes and stabilizes the pasta for handling. The pre-dried pasta moves to a vibrating spreader that distributes it across a mesh belt, feeding into a multi-zone drying chamber. Inside the dryer, temperature, humidity, and airflow are carefully regulated. The first zone heats the pasta to 65-80 degrees Celsius, beginning internal moisture reduction. Airflow alternates above and below the mesh to dry evenly. In the middle zones, humidity is decreased gradually while heat is maintained. This balance prevents surface hardening or internal cracking. The final zone is a cooling section. Here, filtered ambient air lowers the temperature of the pasta to prevent condensation and to prepare it for packaging. Total drying time ranges from 4 to 8 hours, depending on pasta diameter, density, and production volume. The dried macaroni is discharged onto vibrating sieves that remove any undersized or broken pieces. Acceptable product moves by conveyor to a vertical bucket elevator, lifting it into a hopper above the packaging line. From here, pasta is fed into multi-head weighers that release fixed quantities, typically 200g to 400g, into individual pouches. While pasta is being processed, cheese powder mix is prepared in a separate blending operation. Ingredients including dehydrated cheese, whey, milk solids, salt, sodium phosphate, citric acid, and annatto are dosed from stainless steel silos and hoppers into a ribbon blender. The blender combines the powders using overlapping blades that tumble the mix in opposite directions. Uniformity is critical. Each pouch must contain identical flavor and solubility properties. After blending, the cheese powder is sifted through a vibratory screen to remove agglomerates. It is then conveyed to a secondary packaging station. A separate form-fill-seal machine doses a measured amount of cheese powder, typically 20G to 30G, into heat-sealed pouches made from laminated film with oxygen barrier properties. Each pouch is coded with batch and expiration data and conveyed for integration with the pasta. In the combination stage, one pasta pouch and one cheese powder pouch are merged. Collation conveyors synchronize both lines, bringing pasta and cheese pouches together just before cartoning. A horizontal cartoning machine erects cartons from flat blanks, folds the bottom flaps, and holds them open with mechanical fingers. A robotic arm inserts the combined pouches into each open carton. Once filled, the top flaps are closed and sealed using hot melt glue. As cartons exit the sealing station, inkjet printers apply product codes, date stamps, and barcodes. Cameras verify code presence and alignment. Rejected cartons are automatically diverted to a separate line for inspection or rework. Correct cartons proceed to case packing. Cartons are grouped using an inline collator and pushed into a corrugated case supplied by an automatic case erector. Hot glue or tape is applied and the flaps are sealed. Each case passes through a check weigher to verify total contents and is labeled with a print and apply system. The label includes product ID, case count, and tracking data. At the palletizing station, robotic arms stack sealed cases onto wooden pallets. Vacuum pads or gripper arms lift and rotate boxes into aligned layers. Slip sheets are inserted automatically every few layers for added stability. Completed pallets move to a stretch wrapping turntable, where film is wrapped around the load under controlled tension. While packaging is underway, the dry blend operation also prepares bulk cheese powder for institutional or bulk formats. In this variation, cheese mix is loaded into large gusseted bags or drums. Powder filling machines operate under HEPA-filtered enclosures to control dust. Filled bags are sealed with continuous band sealers and printed with lot codes before being packed into master cases. Raw materials for both pasta and cheese powder are delivered in bulk and undergo stringent intake controls. Semolina is tested for protein content, ash level, and granulation. Cheese powder inputs are sampled for moisture, pH, and flavor profile. Silo inventory levels are managed using load cells and level sensors. Water for dough mixing is filtered, UV treated, and temperature controlled. Air used in dryers and conveyors is HEPA filtered and dehumidified. Oil lubricated machinery in contact with product zones uses food-grade lubricants only. All processing equipment is stainless steel, with sloped surfaces and minimal joints to aid cleaning. Production lines are monitored through a central PLC-based control system. Operators use touchscreens to set parameters for extrusion pressure, knife speed, dry temperatures, fill weights, and glue patterns. All parameters are saved in production recipes, enabling rapid line changeovers for different pack sizes or formulations. Extruder head pressure, dough torque, and vacuum levels are logged continuously. Dryer systems include multiple thermocouples and humidity sensors managed by PID loops for responsive control. Air velocity through the drying chamber is measured and adjusted automatically to prevent temperature layering or hot spots. Clean-in-place systems are used to sanitize closed-loop components such as pasta augers, cheese, mix lines, and filler hoppers. Open surfaces are cleaned during scheduled downtime with pressurized water and food-safe detergents. Verification is conducted using swab tests and ATP monitors. Quality control is integrated throughout the line. Pasta is inspected for length, curl radius, color, and residual moisture. Laser micrometers measure wall thickness and internal diameter. Finished pasta is tested for cooking yield, firmness, and disintegration resistance. Cheese powder is evaluated for blend consistency, flavor, and solubility. Random packs are rehydrated and cooked to simulate consumer preparation. Packaging integrity tests include burst tests, seal strength, and vacuum retention for pouches. Cartons undergo drop testing and compression tests to ensure they withstand transit conditions. For single-serve or microwavable mac and cheese, the process begins similarly with pasta production. However, instead of dry packaging, cooked pasta is used. The pasta is first boiled in industrial cookers, long troughs with recirculating hot water systems. After cooking, pasta is cooled rapidly in rotary chillers with cold water spray and air blowers. Cooked pasta is dosed directly into plastic microwavable cups or trays using multi-head filling machines. Cheese sauce, prepared in heated kettles, is pumped into a separate filling head. The sauce is hot-filled immediately after preparation, using servo-controlled pistons that regulate volume and flow rate. After filling, the trays or cups are sealed with foil lids using heated platen sealers. Lidded units are passed through a tunnel pasteurizer, where steam or hot water raises the internal temperature to sterilize the contents. After pasteurization, the products pass through a cooling tunnel with chilled air to bring them to ambient temperature for packaging. Microwavable cups are labeled with shrink sleeves or wraparound labels. Each unit is inspected for fill level, lid seal, and label alignment. These are packed into display cartons, cased, palletized, and shipped with the same downstream systems as dry pack boxes. From raw wheat and powdered cheese to complete boxed or ready-to-eat products, mac and cheese production is a tightly orchestrated process of extrusion, drying, blending, dosing, and packaging. Each component, elbow macaroni and cheese powder, follows a distinct line until their paths converge. Machines extrude thousands of macaroni tubes per minute, slice them, dry them, and screen them into uniform shapes. Ribbon blenders tumble cheese powder until it's perfectly homogeneous. Pouches are filled, sealed, combined, and boxed with mechanical precision. Pepsi begins with water, ordinary in origin, but transformed through an intense purification system. First, the water flows through mechanical filters, stripping out any visible particles. It moves next into activated carbon beds, where chlorine, organic residues, and odors are removed. Then it's pushed through reverse osmosis membranes under high pressure, leaving behind salts, microbes, and trace contaminants. A final sweep of ultraviolet light and ozone leaves the water sterile, mineral-free, and chemically neutral. This is the blank canvas. The next stage injects character. Deep inside jacketed mixing tanks, a thick amber concentrate is created. Liquid sugar surges through stainless steel lines into the tank, met by metered doses of colorants, acids, caffeine solution, and the core flavor compound. Inside the vessel, high-speed impellers shear the mixture into uniformity. The liquid darkens, thickens, and becomes the syrup that defines the drink's signature base. Flow meters and refractometers verify sugar density to the decimal. Agitators spin in controlled bursts. A small shift in temperature or pH would trigger instant correction by the automated control system. Once blended, the syrup doesn't wait. It flows straight into a proportioning unit, where it meets the ultra-purified water. Two pressurized lines merge into one, and precisely tuned valves blend them in a 5-to-1 ratio. The new mixture forms a complete beverage. Almost. First, it's sprayed into a vacuum chamber. This fine mist encounters low pressure and a cloud of CO2. Oxygen is stripped away. The liquid is chilled rapidly to near freezing, lowering its ability to resist carbonation. Inside the carbonation vessel, thousands of microscopic pores inject CO2 with exact pressure. The liquid churns gently in a sealed chamber, held under 4 bar of pressure at 0 to 2 degrees Celsius. Gas dissolves silently. Bubble size, saturation rate, and temperature are monitored in real time. When carbonation reaches target levels, the drink exits the vessel with all of its effervescence locked in. On another line, PET bottle preforms arrive in rapid succession. Each one is gripped by a rotary arm and pass through infrared heaters. The plastic softens and glows dull red before entering the blow mold cavity. High pressure air inflates it in a fraction of a second, pressing it against the steel mold's walls to form a full-size bottle, contoured, clear, and warm to the touch. It exits the mold and cools on contact with the conveyor air. Bottles enter the rinsing carousel, where they're inverted and blasted internally with sterilized water. As they flip upright again, air knives dry the insides instantly. Next, they move toward the isobaric filler, a rotary machine that maintains pressure equilibrium between the drink and the container. Each bottle is clamped beneath a filling valve. CO2 gas is injected first to pressurize the empty space. Then the valve opens and the drink enters from the base, rising smoothly with minimal turbulence. Foam is avoided. Gas is preserved. The moment filling is complete, the bottles roll to the capper. Here, precision torque heads spin blue caps onto each neck. A magnetic clutch delivers exact closing force, tight enough to seal, loose enough to open later. Inline torque sensors confirm every closure. Any outliers are ejected instantly by a compressed air nozzle. From there, each sealed bottle passes under a jet printer that marks it with time, date, and batch code. The ink dries in under a second. A vision system verifies code presence and clarity. Another camera checks fill level and cap alignment. Each bottle is under constant scrutiny as it moves down the line at hundreds per minute. Labels come next. A roll-fed applicator unwinds pre-printed film and cuts each label to size. As bottles spin past, a roller applies adhesive, wraps the label, and smooths it with a brush. The result is a seamless, wrinkle-free appearance with perfect alignment. Sensors detect any offset and make micro-adjustments on the fly. Now grouped into formation, the bottles move toward bundling. A collator arranges them into packs, 6, 12, or 24, depending on the format. Shrink film is draped over each group and heat sealed at the seams. The entire bundle then passes through a shrink tunnel where hot air circulates in tight zones. The film tightens instantly, locking the bottles together in a rigid block. Bundled packs exit the tunnel and head for palletizing. Robotic arms swing overhead, guided by vision cameras and programmed stacking patterns. Grippers lift multiple bundles at once and layer them on wooden pallets. Slip sheets are inserted between tiers by a vacuum-fed arm. Once stacked, the entire pallet is conveyed into a stretch wrapper. A rotating arm winds clear film around the stack in tight spirals, binding the load into one secure shipping unit. Meanwhile, cans run on a parallel line. Massive depalletizers feed columns of aluminum cans into a rinsing tower. From there, the empty cans travel into another isobaric filler designed specifically for pressurized metal packaging. Liquid fills the cans from the bottom. A seamer spins down a lid, hooks the metal under the rim, and crimps it tight. A double seam forms, locking the gas inside with extreme precision. Cans are inverted, jet-coated, vision inspected, and shrink-wrapped in trays. Robotic stackers build them into pallet loads at similar speed to the bottle line. Both packaging lines converge in the same warehouse zone, where outbound conveyors feed the finished pallets toward refrigerated staging docks. Each section of the line is governed by PLCs. These controllers monitor temperature, fill height, carbonation levels, syrup ratios, and packaging counts. Real-time data appears on SCADA terminals, allowing operators to adjust line speed, diagnose faults, and fine-tune performance without stopping production. If any parameter drifts out of tolerance, such as syrup bricks, carbonation pressure, or label alignment, the system either autocorrects or halts the affected module. Clean-in-place systems activate between product runs. Valves switch flow from production mode to cleaning mode. Heated alkaline solution flushes through all contact surfaces, syrup tanks, filler bowls, carbonators, valves, and pipes. Sensors track flow rate and chemical concentration. After the caustic wash, a water rinse clears residue, followed by a sanitizing flush. No disassembly is required. The entire cleaning cycle is automated and logged. During operation, bottle speeds exceed 60,000 units per hour. Carbonation tanks maintain saturation levels within plus 0.05 volumes. Fill levels are accurate to within plus and 1.5 milliliters. Every step, from syrup blending to cap torque, is governed by tolerances and feedback loops. When the process runs at full speed, hundreds of meters of conveyor synchronize bottle spacing, curve speed, and back pressure control. Star wheels, diverters, and sensors ensure smooth flow with no collisions. Air conveyors keep lightweight empty bottles suspended and aligned without touching mechanical guides. Pepsi's production system is built for non-stop performance. Each component, carbonator, blow molder, labeler, filler, capper, bundler, is modular and servo-driven. Changeovers for different bottle sizes or formats require only a software switch, a tooling exchange, and a calibration cycle. The entire system adapts to new production schedules without downtime. Fanta production starts with water, but it cannot be ordinary. The raw supply flows into a filtration system where coarse particles are stripped away. From there, the water passes through activated carbon beds to remove chlorine and organic traces. Next, it enters a reverse osmosis membrane under pressure, separating out salts, metals, and microbes. At this stage, the water is nearly sterile. A final ultraviolet treatment and ozone injection complete the purification. Now the water is neutral, flavorless, and ready for transformation. Inside a stainless steel mixing tank, the drinks base is constructed. A stream of refined liquid sugar is pumped in through insulated lines. Dosing pumps feed in controlled quantities of citric acid, natural fruit flavors, stabilizers, preservatives, and vibrant colorants. The tank's agitators rotate at set intervals to blend the ingredients evenly. Every element is added with exactitude. Flow meters regulate sugar volume. Acid concentration is tracked by inline pH sensors. Color intensity is verified with optical density readers. The mixture is continuously monitored for consistency. Temperature is held between 15 and 20 degrees Celsius. If any reading deviates from target, the control system halts the process and recalibrates dosing in real time. Once the syrup reaches specification, it is transferred to a buffer tank where it rests briefly under agitation, held at a constant temperature and protected from ambient air. Next, the beverage is formed through a high-speed proportioning system. The syrup is combined with the purified water in a fixed ratio, generally around 1 part syrup to 5 parts water. This is managed by synchronized flow meters and control valves. The blending occurs in line, with turbulence in a stainless steel chamber, ensuring rapid and even mixing. The liquid then flows into a de-aeration unit. Inside this sealed vessel, the drink is atomized into fine droplets under vacuum. Dissolved oxygen is extracted while carbon dioxide is introduced. This prevents oxidation, preserves flavor integrity, and prepares the drink for carbonation. Carbonation takes place in a pressurized tank known as the carbonator. Here, the chilled beverage is exposed to a steady stream of carbon dioxide gas. The pressure inside is typically maintained at 3 to 4 bar, and the liquid temperature is kept just above 0 degrees Celsius. These conditions maximize CO2 solubility. Porous stones or fine nozzles distribute the gas, ensuring uniform saturation throughout the tank. Agitators gently rotate to avoid stratification while preventing bubble escape. Meanwhile, packaging lines are activated. If plastic bottles are manufactured on-site, polyethylene terephthalate preforms are loaded into a rotary feeder. Each preform is gripped and passed through an infrared heating oven, where the plastic softens. Inside a blow mold cavity, the preform is inflated with high-pressure air, into its final shape. Bottles emerge, fully formed and warm to the touch. Air conveyors guide them toward rinsing. Rinsers invert each bottle and spray sterile water into the interior. The bottles are then dried with air knives and positioned upright for filling. They enter a rotary isobaric filler, where pressure is equalized between the bottle and the drink to preserve carbonation. Each bottle is locked into a filling valve. First, carbon dioxide gas purges the empty space, preventing oxygen contamination. Then the valve opens and the carbonated Fanta flows upward from the base. Foam is avoided through bottom-up filling and controlled turbulence. When the fill line is reached, the valve shuts instantly. Excess gas is vented and the bottle is released onto the next conveyor. Caps arrive from a centrifugal sorting bowl. They are aligned, sanitized, and fed toward the capper, where a torque head presses and twists each one onto the bottle neck. The torque is monitored by a feedback sensor that checks every closure in real time. Any bottle that fails to meet torque specs is diverted automatically from the line. A high-speed inkjet printer then marks each bottle with production codes, timestamps, and batch identification. These markings are inspected by vision systems that confirm legibility and placement. Additional cameras check fill height and cap alignment. Bottles failing any inspection are rejected through pneumatic actuators. Labeling follows. A roll-fed labeler applies either pressure-sensitive or glue-applied labels depending on the format. The label roll unwinds, cuts to length, and wraps each bottle in a single smooth motion. Rollers press out any air bubbles, and sensors verify label position. Adjustments are made automatically based on visual feedback. Labeled bottles are grouped into packs at the bundling station. A servo-controlled collator arranges them into 12s, 6s, or 24s depending on product format. A plastic shrink film wraps around the group, and the pack passes through a heat tunnel. Hot air shrinks the film tightly, locking the bottles into a unified pack. The packs move on to palletizing. A robotic arm with suction cups or mechanical clamps picks up each bundle and stacks it on a pallet in alternating patterns. Slip sheets are added for stability. Once a pallet is full, it's moved into a stretch wrapper. A rotating arm wraps plastic film under tension from the base to the top of the stack. This secures the load for transport. Parallel to the bottle line, aluminum cans are processed on a separate track. Empty cans arrive by depalletizer and enter a rinser. After internal cleaning, they flow into a high-speed rotary filler. Isobaric pressure filling minimizes gas loss. Immediately after filling, the cans pass into a seamer where a metal lid is dropped and double seamed with extreme force and precision, sealing in the carbonation. Cans are coated, checked, and shrink wrapped into trays, then palletized, just like bottles. Every mechanical step is governed by programmable logic controllers. These devices receive data from sensors monitoring flow rates, temperatures, torque values, fill levels, and carbonation pressure. If any parameter drifts beyond tolerance, the system adjusts in real time or stops the line. All systems communicate through a central SCADA interface, which displays status updates, alarm logs, and production metrics. Carbon dioxide is supplied from insulated bulk tanks located outside the plant. The gas enters the process through a vaporizer and filtration unit. Inline pressure regulators and flow restrictors ensure stable CO2 supply at all stages, from de-aeration to final carbonation. Clean-in-place systems activate between production cycles. A series of automated valves switch flow from product to detergent solution. Heated caustic cleans the tanks, pipes, carbonator, and filler valves. A rinse follows, and finally, a sanitizing solution is circulated. No disassembly is required. The process is monitored by conductivity meters and temperature sensors to verify cleaning effectiveness. Each segment of the Fanta production line is built for modularity and speed. Conveyor belts stretch across the plant in smooth arcs, synchronized by servo motors. Air conveyors are used in bottle transport to prevent mechanical contact. Accumulation zones between machines allow buffer space, so the line continues running even if one unit slows down. Production speeds for bottles can exceed 60,000 units per hour. Lines can operate at over 120,000 units per hour. The entire system is balanced to prevent bottlenecks. Fillers, labelers, and palletizers adjust their speed based on feedback from downstream equipment. Fill level is controlled to within 1.5 milliliters. Carbonation is regulated within a tolerance of 0.05 volumes of gas. Cap torque is checked to within 1 Newton meter. These tolerances are enforced by constant feedback and precision sensors. Label alignment is maintained through optical recognition. If the label wanders off-center by more than 2 millimeters, the labeler adjusts roller speed and cutter timing. Bundling film is tension controlled to avoid wrinkles or tears. Shrink tunnels have multi-zone heating, each controlled by thermocouples. Fanta's bright appearance comes from precise color dosing. The colorant solution is metered by mass flow controllers that inject it directly into the syrup blend. Any deviation in hue is detected by an inline spectrophotometer. For different flavors and regions, flavor concentrate tanks are changed out through quick connect valves. Each tank is barcoded, and the system will not run unless the correct flavor for the scheduled run is confirmed. All ingredient additions are logged, time-stamped, and tracked through the control network. Dr. Pepper begins with purified water. Municipal or well-sourced, the incoming supply is routed through a multi-stage treatment system. First, it flows through coarse filters that remove sediments and suspended particles. Then it enters activated carbon beds, which strip chlorine, off flavors, and organic traces from the water. Next, the liquid is pumped through a reverse osmosis membrane under high pressure. This removes dissolved minerals, bacteria, and microscopic contaminants. Final disinfection is completed using ultraviolet light and ozone. The result is neutral, sterile water, continuously recirculated through stainless steel holding tanks to maintain freshness and prevent stagnation. Inside the syrup room, Dr. Pepper's base formula is built in a precision blending tank. Liquid sugar, delivered in insulated tankers, is pumped into the tank through flow-regulated stainless lines. Into this stream, concentrated acids, natural and artificial flavors, colorants, and preservatives are dosed through servo-driven valves. These ingredients are not added all at once, but follow a timed sequence governed by a central control system. Stirring paddles agitate the mixture at programmable speeds. Viscosity sensors monitor the syrup's thickness. A pH probe verifies acid levels. An inline refractometer measures sugar concentration down to 1/10 of a Brix unit. As the mixture blends, the syrup's consistency is adjusted by adding chilled water or holding the solution under vacuum to prevent oxidation. Dr. Pepper's distinct flavor comes from a complex mix of flavor oils and acids, blended in sub-milliliter quantities by a dedicated dosing module with flow control down to microliters. Once all parameters are within specification, the syrup is held in a buffer tank under sealed conditions, continuously stirred and maintained at a stable temperature. Syrup is then piped into a proportioning unit where it meets the purified water in exact ratios. Typically, 1 part syrup is mixed with 5 parts water. Flow meters and precision control valves adjust the inputs in real time, ensuring consistency throughout the production run. This mixing takes place inside a turbulence chamber designed for immediate homogenization. The freshly blended beverage passes through a deaeration chamber. Here, the liquid is atomized under vacuum, breaking it into tiny droplets. This process removes dissolved oxygen that would otherwise cause off flavors or affect carbonation retention. Simultaneously, carbon dioxide gas is injected into the chamber to further displace any remaining oxygen. The temperature is dropped below 5 degrees Celsius to prepare the drink for carbonation. Carbonation takes place in a pressurized stainless tank fitted with high-efficiency gas diffusers. The beverage is injected with food-grade carbon dioxide at controlled flow rates. Pressure is held steady between 3 and 4 bar, while temperature is maintained just above freezing. Agitators inside the tank rotate slowly, ensuring uniform CO2 saturation without causing foaming or loss of gas. Carbonation level is verified with an inline CO2 analyzer calibrated to within 0.05 volumes of gas. While the beverage is being carbonated, packaging operations are running in parallel. On the bottle line, polyethylene terephthalate preforms are fed into a rotary blow molder. Each preform is picked up by a gripper arm and passed through infrared heaters. When the plastic softens to the ideal temperature, it is transferred into a mold. High-pressure air inflates it rapidly, pressing it into the mold cavity and forming the final bottle shape. The molded bottle is immediately cooled and conveyed onward by air track systems that minimize surface contact. At the rinsing station, bottles are inverted and blasted with sterile water or filtered compressed air. After rinsing, the bottles are uprighted and fed into an isobaric rotary filler. This machine equalizes the internal pressure of the bottle with that of the carbonated beverage, minimizing gas loss during filling. Each bottle is clamped into a filling turret. A burst of CO2 is injected first to displace any residual air. Then the valve opens and liquid enters from the bottom. As the beverage level rises, gas is displaced upward and captured. Fill level sensors detect the target point, and the valve shuts instantly. The bottle rotates out and moves to the capping unit. Caps are sorted and oriented by centrifugal feeders. They are sterilized in line and delivered to the capping head, where servo-driven torque applicators screw them onto the bottleneck. Torque is measured in real time. Each closure is verified for tightness and alignment. If torque deviates from specification, the bottle is automatically rejected. After capping, the bottles move under an inkjet printer. Here, date codes, batch numbers, and production timestamps are applied to the shoulder or neck of the bottle. High-resolution cameras inspect the print for clarity and accuracy. Another vision system scans the bottle for correct fill level, cap integrity, and label presence. Labeling occurs at high speed. Rolls of pre-printed labels are fed into a rotary applicator. As each bottle rotates past, a servo-controlled arm presses the label onto the surface using adhesive or heat. Rollers smooth the label, edge to edge. A laser eye checks label alignment and triggers adjustments if needed. Labeled bottles are grouped at the bundling section. Depending on the product format, bottles are organized into groups of 6, 12, or 24. A clear shrink film wraps the cluster, and the bundle moves through a hot air tunnel. Controlled heating zones shrink the film tightly around the bottles without warping or melting. Next, the shrink-wrapped bundles are transported to the palletizing area. A robotic arm equipped with vacuum grippers picks up each bundle and stacks it onto a pallet following a programmed pattern. Slip sheets are inserted between layers to add friction and prevent collapse during transport. Once the pallet is complete, it is conveyed to a stretch wrapper. A rotating arm encircles it, applying plastic film from bottom to top. Film tension is automatically adjusted based on load profile and height. Parallel to the bottle line, the can line operates with higher throughput. Empty aluminum cans are depalletized and fed into a high-speed rinsing tower. After rinsing, cans enter a rotary filler similar to the one used for bottles, but designed specifically for metal packaging. The carbonated Dr. Pepper is injected under pressure. Immediately afterward, lids are placed on the cans and sealed with a double seamer. This forms an airtight seal between the lid and the can body. Cans are inverted, coated with inkjet printers, and inspected by a multi-camera system. Approved cans are organized into trays or shrink-wrapped into multi-packs. Robotic palletizers stack the finished units onto pallets. Final pallets are labeled, wrapped, and staged for shipping. Throughout the process, programmable logic controllers coordinate every movement. Each section of the line operates independently but communicates through the central control system. SCADA terminals show live readouts of temperature, pressure, line speed, fill volume, syrup ratio, carbonation level, and product counts. Alarms and trend logs are automatically stored for quality assurance. Carbon dioxide is supplied from an external cryogenic tank. The liquid gas is vaporized and filtered before entering the production system. Flow meters and pressure regulators maintain steady gas delivery to the de-aeration and carbonation units. Backup systems ensure uninterrupted flow. Clean-in-place systems operate at the end of each production run. Automated valves redirect flow through all product contact surfaces. Heated caustic detergent is pumped through tanks, pipes, fillers, and carbonators. A water rinse follows, and then a sanitizing solution is circulated. Conductivity and temperature sensors confirm cleaning efficiency. The entire cleaning sequence is logged and time-stamped. Dr. Pepper production lines are built for speed and adaptability. The blow molder can be adjusted for different bottle volumes. The labeler and filler can switch formats through software changes and tool-free part swaps. Servo motors drive most critical systems, allowing rapid changeovers with high accuracy. Filling accuracy is controlled to within 1.5 milliliters per container. Carbonation tolerance is held within 0.05 volumes of CO2. Cap torque is measured to within a fraction of a Newton meter. Label alignment deviation is limited to 2 millimeters. Every product is subjected to multiple points of verification before it leaves the line. Accumulators between machines allow for variable speed balancing. If a downstream unit slows, upstream conveyors store excess product temporarily. This prevents system shutdowns and maintains steady throughput. Conveyors are fitted with contactless sensors that monitor spacing and position, allowing real-time speed adjustment without collisions or jams. From raw water intake to final pallet wrapping, every phase of Dr. Pepper production is controlled, calibrated, and continuously monitored. No step is isolated. Syrup formulation, carbonation, filling, labeling, coating, packaging, and palletizing are integrated into a seamless flow of motion, temperature, pressure, and precision. Producing 10 million Snickers bars begins with raw ingredients delivered in industrial-scale volumes. Liquid glucose, granulated sugar, skimmed milk powder, cocoa liquor, cocoa butter, vegetable fats, peanuts, egg white, lactose, and emulsifiers. All materials are stored in temperature-controlled silos, tanks, or hoppers, connected by stainless steel pipelines and pneumatic conveyors to feed the production lines with uninterrupted flow. The first step is the nougat base. A pre-blend of sugar, glucose syrup, and water is piped into a continuous cooker. This cooker operates under controlled heat and vacuum, rapidly boiling the mixture to reach the target solid's content while minimizing color and flavor degradation. The hot syrup exits at around 120 degrees Celsius and is sent straight into a high-speed whipping chamber. Inside the whipper, dried egg white and milk powders are injected. A rotor-stator system beats the mix at high speed, incorporating air into the matrix to create the nougat's aerated structure. The density is tightly regulated with inline sensors measuring viscosity and expansion ratio in real time. Once aerated, the warm nougat mass flows through heated stainless steel pipes and is deposited as a continuous sheet onto a wide belt coated with a release film. As the sheet advances, calibrated rollers compress it to a uniform height, typically between 12 and 15 millimeters. The sheet then passes through a cooling tunnel that drops its internal temperature below 20 degrees, stabilizing the structure for the next layer. Once cooled, the caramel layer is applied. Caramel production occurs in a separate closed-loop cooker, where a mixture of glucose syrup, sugar, dairy fats, and milk solids is cooked under vacuum to reach the desired viscosity and chew. The caramel exits the cooker at around 118 degrees and flows into a depositing manifold. This manifold lays a smooth, uniform layer of hot caramel directly onto the nougat sheet. While the caramel remains soft, whole roasted peanuts are added. Peanuts, sourced in bulk, are first passed through an inline sifter to remove debris, then lightly roasted in continuous rotary ovens. After roasting, they are cooled and metered onto the caramel layer using a vibratory conveyor with adjustable baffles. The conveyor distributes peanuts evenly across the moving sheet, ensuring every section contains a balanced nut density. The peanut caramel nougat tri-layer now proceeds through a final compression roller, bringing it to the finished bar thickness. From here, the slab enters a chilling tunnel that gradually reduces its temperature from ambient to below 10 degrees C over a span of 20 meters. This ensures the caramel sets just enough to be cleanly cut without oozing or deformation. After chilling, the slab moves to a guillotine cutter. First, rotary blades cut it lengthwise into continuous ribbons, each the width of a Snickers bar. Then, a high-speed guillotine slices each ribbon into uniform bar-sized segments using servo-controlled motion synchronized with the belt speed. Blades are coated with a non-stick surface and cleaned automatically to prevent buildup. Each freshly cut bar now enters the enrobing stage. Bars are transferred onto a wire mesh conveyor belt and passed beneath a curtain of tempered milk chocolate. This chocolate is continuously circulated through a 3-stage tempering system, where it is heated, cooled, and reheated to create stable cocoa butter crystals. The chocolate is maintained at 30 to 37 degrees Celsius, ensuring proper viscosity and flow. As each bar passes through the enrober, it is coated on all sides, top, bottom, and flanks. The base of the bar receives a bottoming layer of chocolate from a pre-flooded section of the belt. Excess chocolate is removed by an adjustable air knife that blows a focused jet across the bar's surface, shaping the characteristic swirl patterns on top. A vibrating section under the mesh belt removes bubbles and smooths the surface. The enrobed bars enter a cooling tunnel that spans 30 meters and consists of multiple zones. Each zone gradually reduces the air temperature, allowing the chocolate to crystallize evenly. The final zone chills the bars to below 8 degrees Celsius, locking the coating into a firm, glossy finish with the correct snap and bloom resistance. After exiting the tunnel, each bar is inspected by a vision system. High-resolution cameras scan every unit for shape, surface quality, alignment, and chocolate coverage. Defective bars, those with missing peanuts, air gaps, or surface defects, are automatically rejected through pneumatic diverters. Accepted bars move on to the wrapping section. Each bar is fed into a flow wrapping machine running at speeds of up to 100 bars per minute. Wrapping film, pre-printed with branding and batch codes, is drawn from a roll and cut to size by rotary knives. As each bar passes through, it is wrapped in film, heat-sealed along the underside, and crimp-sealed at both ends. The sealing jaws operate with synchronized thermal and pressure settings to create tight, tamper-proof packages. Wrapped bars are conveyed through a metal detector, calibrated to detect both ferrous and non-ferrous contaminants. Any bar triggering the system is rejected. Compliant bars continue to the check weigher, which confirms unit weight to within plus and 1.5 grams. Any deviation results in immediate removal from the line. The verified bars are then grouped and collated. Robotic arms pick up sets of bars, typically 24, 36, or 48, and place them into cartons automatically erected from flat, blanks, Hot melt glue is applied by precision nozzles to secure the flaps. Cartons are closed, sealed, and printed with best before dates using high-speed inkjet coders. Cartons then advance to the palletizing station. Here, robotic palletizers arrange the cartons into stacks on standard Euro or GMA pallets, using a pre-programmed pattern that alternates layer direction for stability. Slip sheets are inserted automatically between layers. Once a pallet is complete, it is wrapped with stretch film by a rotating arm that applies the film under tension to create a rigid, transport-stable unit. Throughout the entire process, programmable logic controllers coordinate equipment motion, timing, and feedback across the line. Each machine is connected to a centralized SCADA system that logs production metrics, sensor values, fault codes, and output counts in real time. Operators monitor touchscreen panels displaying temperature trends, motor speeds, belt loads, fill levels, and inspection alerts. The chocolate tempering unit is governed by 3 separate thermal zones, each independently controlled by thermocouples and heating elements. Syrup bricks is measured inline using optical refractometers. Nougat density is monitored by in-pipe density meters. Caramel viscosity is controlled by adjusting vacuum level and cook temperature. Every variable is closed-loop controlled, meaning it adjusts itself based on sensor readings. Carbon dioxide is used in modified atmosphere packaging for bulk storage formats. The gas is injected into large multi-bar containers to displace oxygen, extending shelf life. These containers are flushed, sealed, and stored in chilled holding bays before being distributed. Clean-in-place systems automate sanitation. Heated caustic detergent flows through all nougat, caramel, and chocolate handling systems at the end of each run. Pipes, tanks, depositors, and pumps are cleaned in sequence, followed by hot water and sanitizing rinse. Each cycle is logged with flow rate, contact time, and temperature. To produce 10 million Snickers bars, the line operates continuously for multiple days across several parallel lines. A single high-speed line can produce up to 1,100 bars per minute. With 10 such lines running in tandem, nearly 720,000 bars are produced per hour. In under 14 hours, 10 million bars are complete. Each bar is mechanically identical. Same mass, same shape, same structure. From aerated nougat to sticky caramel, crunchy peanuts, and smooth milk chocolate coating, the process controls every variable. Flow meters, torque sensors, load cells, vision cameras, pH probes, temperature controls, and synchronized motors maintain the consistency required for mass production. Every action is automated, but none is simple. The caramel must flow, but not run. The nougat must hold its structure without hardening. Peanuts must fall in even distribution without clumping or rolling. Chocolate must be tempered, coated, shaped, and solidified, without bloom, swirl misalignment, or trapped air. Producing 10 million Reese's peanut butter cups begins with the bulk delivery of core ingredients: roasted peanuts, cocoa liquor, cocoa butter, sugar, salt, milk solids, dextrose, emulsifiers, and stabilizers. Raw materials arrive in tankers, super sacks, and silo containers, and are fed into the production system via automated pneumatic transfers, conveyor augers, or liquid pumps, all connected to centralized control systems that regulate flow, temperature, and mass. The peanut butter core is produced first. Whole roasted peanuts are delivered directly into an industrial-size vibrating hopper. The hopper separates debris, splits, and undersized fragments through a combination of screen grating and air jets. The selected peanuts are passed through a second roasting stage in a continuous rotary drum oven, bringing their internal temperature above 160 degrees C. This ensures uniform oil release and deepens flavor. As they exit the roaster, the peanuts are immediately cooled using a forced air cyclone system to prevent over-roasting. Cooled peanuts are fed into a hammer mill, where rotating steel blades grind them into a fine, warm paste. The paste flows directly into a ribbon blender, where sugar, salt, dextrose, and stabilizers are added. The blender's high shear paddles fold and mix the ingredients, creating a thick, creamy filling with a controlled moisture content and spreadable viscosity. Viscosity sensors and torque meters monitor the blend in real time. The finished peanut butter is pumped into heated jacketed holding tanks equipped with agitators that keep the filling homogeneous and at a stable flow temperature around 45 degrees Celsius. Meanwhile, chocolate production runs in parallel. Cocoa liquor, cocoa butter, sugar, milk solids, and lecithin are fed into a high-capacity conche. The conche kneads and heats the mixture, allowing moisture and acidity to evaporate. Internal temperature is held between 50 °C and 60 °C. Once the flavor has developed and the texture has been refined to a smooth mass, the mixture is transferred to a 5-roll refiner. In the refiner, steel rollers shear the chocolate mass to reduce particle size to below 20 microns. The refined chocolate is then conched again to polish the particle surfaces, improve flow, and enhance melt. From the conche, the liquid chocolate is pumped through heat-maintained stainless lines into tempering units. Tempering machines cycle the chocolate through 3 thermal zones: heating to fully melt all crystals, cooling to encourage stable seed crystal formation, and reheating to melt unstable forms. The result is chocolate with stable beta crystals that produce a glossy finish and crisp snap. Now the forming line is activated. Pre-formed paper cups are dispensed from a magazine feed into indexed molds on a conveyor belt. A depositor head descends over each cup and fills the base with a measured dose of tempered chocolate. This forms the bottom, shell. As the chocolate hits the cup, the molds are vibrated rapidly, forcing the liquid to spread evenly and coat the cup base. The conveyor then carries the partially filled cups through a cooling tunnel that drops the chocolate temperature to around 10 degrees Celsius over several minutes, solidifying the shell and contracting it slightly away from the paper wall. Next, the peanut butter filling is applied. A piston depositor, aligned with the mold indexing system, dispenses a precise slug of peanut butter directly onto the cooled chocolate base. The volume is tightly controlled, typically 10 to 15 grams per cup, depending on size variant. The warm filling spreads slightly on contact, but retains its form due to its balanced fat structure and cooling effect from the base. A brief second cooling tunnel pass stabilizes the core enough to support the top chocolate layer. The top layer of chocolate is deposited last. Another depositor head applies a final pour of tempered chocolate over the peanut butter core. Vibration removes any trapped air and flattens the surface to an even plane. This final deposit seals the core entirely, forming the completed cup. The filled cups now pass through the primary cooling tunnel, a multi-zone chamber that gradually drops the internal temperature of each cup to ensure uniform crystallization. Airflow, humidity, and conveyor speed are precisely tuned. The full cooling cycle lasts around 10 minutes, allowing the chocolate to fully solidify without forming sugar bloom or fat migration marks. As the cups exit the tunnel, they undergo automated inspection. Vision systems scan every unit for fill height, surface uniformity, and alignment within the paper cup. Cups with off-center deposits, cracked surfaces, or exposed peanut butter are automatically rejected by robotic arms or pneumatic gates. Approved cups continue to the wrapping station. A pick-and-place system lifts each cup and transfers it to the wrapping infeed. Wrapping film, pre-printed with branding and registration marks, is cut to size and wrapped tightly around each cup using a twist wrapping mechanism. The ends are pinched and twisted shut by synchronized spinning belts. Wrapping speeds can exceed 1,000 units per minute per line. Wrapped cups are conveyed through a metal detector calibrated for high sensitivity to both ferrous and non-ferrous contaminants. Any package triggering an alert is automatically diverted. Cleared products are grouped into collating lanes. Collators arrange cups into blister trays or multi-packs. A robotic grouping arm aligns sets of cups and loads them into thermoform trays or folding cartons. These cartons are pre-formed in a high-speed erector. Hot melt adhesive is applied to flaps, and cartons are sealed using servo-driven compression plates. Cartons are printed with date codes and batch numbers using thermal inkjet or laser coders. Completed cartons move toward the palletizing area. Robotic palletizers lift cartons using vacuum, grippers or adjustable forks, and stack them onto wooden or plastic pallets in a fixed interlocking pattern. Slip sheets may be added between layers. Each full pallet is conveyed to a stretch wrapper. A rotating arm applies film from bottom to top, binding the load securely for transportation. All stages are governed by programmable logic controllers. Each machine communicates via industrial Ethernet to a centralized control room. SCADA interfaces display real-time production data, including belt speeds, depositor accuracy, wrapping count, rejection rates, temperature profiles, and chocolate viscosity. Ingredient dosing is closed-loop controlled. If sugar concentration drifts in the peanut butter mix, the feeder corrects flow automatically. Chocolate viscosity is monitored using inline rotational viscometers. Fill weights are verified by high-speed load cells. Position sensors and servo motors keep all timing synchronized across multiple parallel lines. Each line is designed for continuous operation. Changeovers are handled with tool-less part swaps and automated cleaning sequences. Clean-in-place systems, wash tanks, pipes, and depositors between shifts. Heated caustic detergent is pumped through all product contact lines, followed by a water rinse and final sanitizing flush. Flow rate, contact time, and return temperature are logged and verified automatically. Producing 10 million peanut butter cups requires multiple synchronized lines running at high throughput. A single high-speed line can produce over 1,200 units per minute. 10 such lines operating in parallel generate 720,000 units per hour. In a continuous run, lasting just under 14 hours, the full batch of 10 million is completed. Each cup is mechanically identical. Same chocolate mass, same peanut butter volume, same shell thickness, same twist wrap tightness. The consistency is achieved through calibrated depositor nozzles, servo-actuated plungers, precision-heated tanks, and closed-loop feedback across every stage of production. Key tolerances are maintained. Chocolate fill weight within plus as 0.5 grams, peanut butter center within plus 1 millimeter of alignment, wrap tension within 2%, seal temperature within plus 1.5 degrees Celsius. Rejects are tracked and analyzed automatically to detect trends before they cause system-wide variation. Temperature is crucial. Chocolate crystallization, peanut butter viscosity, cooling tunnel performance. Every step is sensitive to thermal drift. Thermocouples monitor all zones, from tanks to tunnels. If any zone deviates from range, alarms sound and the affected section is automatically adjusted or stopped. From the peanut grinding to the pallet wrap, the process is fully integrated. There are no idle steps. Syrup mixing, shell forming, core deposition, sealing, cooling, inspection, wrapping, cartoning, and palletizing flow in continuous sequence. There is no manual intervention. Everything moves in rhythm, guided by sensors, actuators, and control algorithms. Producing 10 million M&Ms begins at the granule level. Core ingredients like sugar, cocoa mass, cocoa butter, milk solids, corn syrup, and food-grade colorants are delivered in bulk. Each component is unloaded into stainless steel silos, insulated storage tanks, or vacuum-sealed hoppers. From there, pneumatic conveyors and positive displacement pumps transfer the raw materials into the processing line with exact flow control. Every ingredient is monitored by mass flow meters, auger dosing systems, and load cell integrated vessels to ensure accurate, repeatable input ratios. The first major step is creating the chocolate centers. These are not flat discs to start with. They begin as lentil-shaped chocolate pieces, formed, cooled, and prepared for shell coating. Chocolate production occurs in a multi-step blending and refining system. Liquid cocoa liquor, cocoa butter, and sugar are pumped into a conche. In this high-shear mixing chamber, ingredients are heated and agitated over hours, reducing acidity and moisture while developing flavor. The mass then flows into a 5-roll refiner. This machine crushes the chocolate through narrowing steel rollers until particle size falls below 20 microns, producing the creamy texture needed for M&M's centers. The refined chocolate returns to a second stage conche for additional smoothing. From the conche, the chocolate mass is pumped through jacketed pipes into tempering units. These systems rapidly cycle the chocolate through heating, cooling, and controlled reheating phases, encouraging the formation of stable cocoa butter crystals. Tempered chocolate exits at a tightly maintained viscosity and temperature, ready for molding. The molding system produces the core. Individual chocolate lentils are formed by depositing droplets of tempered chocolate onto a chilled belt. As each droplet lands, it spreads slightly before solidifying into the iconic disc shape. High-speed vibratory tables level and settle each piece before the belt enters a rapid cooling tunnel. Cold air circulates above and below to ensure uniform hardening. Each M&M-sized piece is checked by laser sensors for thickness and diameter tolerance. Once solidified, the chocolate cores are collected into stainless steel bins and conveyed to the panning room. Here begins the defining process. Sugar shell coating through precision, layering in automated panning drums. The panning drums are large rotating cylinders with polished stainless interiors. Thousands of chocolate cores are loaded into each drum. As the drums rotate, a fine mist of sugar syrup is sprayed through atomizing nozzles. The syrup is a concentrated mix of sugar, glucose, and water, heated to remain fluid but not overly thin. The chocolate cores tumble while the syrup coats them evenly. Cold, dehumidified air is blown into the drum chamber to dry each layer. This process is repeated across dozens of cycles. Each round adds a thin sugar layer. The rotation angle, drum speed, airflow, syrup volume, and spray pattern are all programmable and adjusted in real time by feedback systems. The cores grow gradually, layer upon layer, until the shell thickness reaches the target range. Throughout the panning process, non-contact sensors monitor shell diameter growth. Cameras detect shape anomalies or cracks. Any defective units are removed automatically using vibration sorters and size classifiers. After achieving the proper shell thickness, the final stage of the sugar coating is the polishing sequence. Polishing begins with a thin application of carnauba wax and food-grade glaze. These are sprayed inside the rotating drum, creating a slick coating on the sugar shells. Buffing arms inside the drum press and polish the surface as it spins, producing the high-gloss finish M&Ms are known for. The shine is not just cosmetic, it also protects the candy shell from humidity and reduces friction during packaging. Now, the finished M&Ms are conveyed into the color coding system. The distinctive red, yellow, blue, green, orange, and brown shells are not coded one at a time. Instead, batches are divided and each drum is designated for a specific color. Colorant solutions, made from water-soluble dyes and a sugar base, are sprayed into the rotating drum in much the same way as the shell syrup, but in smaller quantities. The dyed layers are dried with a gentler airflow to prevent streaking or pooling. After color coding, another pass of polishing glaze is applied for clarity and shine. After drying, M&Ms are released onto vibrating conveyor belts. These belts sort the pieces, prevent sticking, and align them into single-file lanes for printing. A laser-guided inkjet system prints the signature M on each piece. Optical sensors locate the center of each candy and trigger the inkjet nozzle to fire the white food-grade ink at exactly the right spot. The print dries in under 1 second using forced air and low heat. The print tolerance is within 1 millimeter per piece. Any candy without a printed M or with a misprint is identified by high-resolution cameras and removed from the stream. Printed M&Ms pass through a metal detector that scans for ferrous, non-ferrous, and stainless steel contaminants. They then flow into a check weigher, which confirms the average weight of grouped candies matches the package specification. If the weight falls outside a narrow band, that group is rejected. Now the candies are funneled into packaging units. Depending on the format, single-serve pouches, theatre boxes, tubes, or multi-packs, the M&Ms are guided through volumetric fillers, counting systems, or load cell-based dosing mechanisms. For pouches, horizontal form-fill-seal machines draw roll-fed plastic film, print batch codes, and form it into bags. A vertical chute dispenses a fixed volume of M&Ms into each bag, which is then sealed with a heated jaw. For boxed formats, cartons are formed from flat blanks by a mechanical erecting arm. Pre-grouped M&Ms are poured into the boxes using funnel-shaped hoppers with vibratory feeders to ensure consistent flow. Boxes are sealed using hot melt glue and compressed under pressure for final closure. All packages are marked with laser-etched batch codes and expiration dates as they exit the system. Finished packages move on to conveyor belts toward the robotic palletizing area. Here, industrial robots equipped with vacuum pads pick up multiple units at once and stack them in program formations onto wooden pallets. Slip sheets are inserted automatically for stability. Once stacked, the pallet moves to a stretch wrapping unit. A rotating arm applies plastic film tightly around the load to prepare it for distribution. To reach 10 million units, the process relies on multiple parallel lines. Each high-capacity line can produce more than 2,000 pieces per second. With 10 synchronized lines running continuously, the factory generates 72,000 pieces per second, over 4.3 million per minute. In just under 40 minutes, the full 10 million pieces are completed, each one identical in size, shape, coating, gloss, and print. All steps are governed by programmable logic controllers. The entire factory is coordinated through a distributed control system, with real-time SCADA dashboards showing every variable: syrup viscosity, shell thickness, air humidity, shell growth rate, rotation speed, dye concentration, gloss level, printing accuracy, and package weight. Sensors monitor the production line at every point. Shelling drums use load cells to detect overfill. Thermocouples track temperature inside conchis, tanks, and coating units. Flow meters control syrup delivery. Cameras confirm print legibility. Servo motors handle belt timing, robotic arm movement, and package alignment. Cleaning cycles run automatically between batches. Sugar lines, chocolate tanks, conchis, panning drums, and depositor heads are cleaned using hot, circulating detergent, followed by high-pressure rinses. All cleaning steps are validated by chemical conductivity sensors and logged for traceability. The factory layout is linear but modular. Chocolate production, shell coating, coloring, printing, and packaging are linked by buffer zones that allow for surge capacity. If one stage slows, others continue without shutdown. Every section has redundant machinery to allow for changeovers and maintenance. Tolerance ranges are tight. Shell thickness must fall within +0, 15 millimeters. Chocolate center weight must remain within +0.2 grams. Printing alignment cannot vary more than 1 millimeter. Shell color concentration is monitored by spectrophotometers to ensure consistency across millions of pieces. Every variable, from syrup crystallization to drum angle to print timing, is calibrated for absolute uniformity. This level of precision ensures that 10 million M&Ms are not just mass-produced, but identically produced. Each one carries the same shine, the same crunch, the same chocolate-to-shell ratio, and the same instantly recognizable M. From grinding cocoa to molding chocolate, from layering sugar to polishing glaze, from color batching to robotic stacking, the process never stops. The result is a continuous stream of motion, heat, rotation, and control, where every piece, every shell, and every package flows through the system in perfect mechanical choreography. The process for Haribo gummy bears starts in the dissolving room, where glucose syrup and granulated sugar are pumped and conveyed into a heated stainless steel vessel. This vessel, fitted with high-speed agitators and a triple-wall steam jacket, maintains constant agitation while heating the syrup mixture to around 110 degree cup walks. The goal is to dissolve the sugar completely and create a smooth, viscous base. Flow meters and density sensors monitor the syrup's solids content and concentration in real time. Once dissolved, the hot sugar solution is pumped into a vacuum cooking chamber. Here, under reduced pressure, the solution is further concentrated and residual moisture is removed. The vacuum environment allows water to evaporate at lower temperatures, preserving the integrity of thermally sensitive ingredients like flavorings and gelatin to be added later. The cooked syrup exits the vacuum chamber at a high Brix level, typically 78 or 80% solids. Gelatin, a key component of gummy bear texture, is processed separately. It is first weighed and hydrated in a pre-mixing tank, where it soaks in cold water under gentle agitation for several hours. This allows the gelatin to swell and dissolve fully. Once hydrated, the gelatin slurry is gently warmed to 60-70 degrees Keys and held in a circulation loop to maintain its viscosity and flow properties. Agitation is constant but low shear, preserving the molecular structure essential for the signature gummy chew. The concentrated sugar glucose syrup and the liquefied gelatin are metered into a dynamic mixing vessel. In this unit, the two streams are blended under vacuum to prevent air bubbles. Inline emulsifiers introduce fruit juice concentrates, plant-based colorants, citric or malic acid, and flavor oils. These are injected at precise intervals using servo-controlled diaphragm pumps. Optical clarity, pH, viscosity, and temperature are continuously monitored and regulated. The entire mixture forms a uniform candy mass with a temperature between 75 degrees Celsius and 85 degrees to create multiple flavor variants. The unified base is split into smaller batches and pumped into separate flavor ash color blending tanks. Each tank is dosed with its assigned fruit flavor and colorant: strawberry, lemon, orange, raspberry, apple, pineapple, each controlled by automated recipe software. Once blended, each colored candy mass is held in jacketed kettles that maintain temperature and prevent settling. The molded shaping process begins with starch preparation. Cornstarch trays, shallow wooden or plastic frames filled with fine cornstarch, are first leveled and dried. These trays pass under a starch molding board fitted with multiple metal stampers shaped like gummy bears. The stampers press into the starch, leaving behind thousands of negative impressions. The flavored candy mass is deposited into these starch impressions by a multi-head depositor. This machine uses pneumatic or servo-driven nozzles to fill each cavity with a precise volume of hot liquid candy. Each nozzle is temperature controlled to maintain candy flow without crystallization or gelation. The depositor can move in synchronized XY motion, matching the layout of cavities in the starch bed. Depositing speed exceeds several hundred rows per minute. Once filled, the trays are conveyed into a controlled environment curing room. Here, over a period of 24 to 72 hours, the gummy candy sets and matures. During this time, the gelatin network fully develops, moisture migrates, and the candy reaches its final elasticity. Room conditions are tightly regulated, typically at 20 to 25 degrees with 15 to 25% relative humidity. Airflow is carefully balanced to avoid uneven drying, and trays are rotated periodically. After curing, the gummy bears are removed from the starch using a tray inversion system. Trays are flipped onto a vibrating sieve table, and the bears fall free from the starch. Remaining starch is separated via vibration and aspiration, and returned to the starch storage system for drying and reuse. The gummy bears are now fully formed, but covered in a thin layer of starch dust. The bears enter the cleaning stage. First, they are conveyed through a rotary drum fitted with soft brushes and low-pressure air jets to remove starch residue. Next, they are transferred into an oiler drum. Here, the gummies tumble slowly while being misted with a thin layer of food-grade oil, such as carnauba wax or mineral oil. This coating gives them their glossy appearance, prevents sticking, and enhances mouthfeel. Rotation speed and spray intensity are precisely regulated to ensure uniform coverage. Polished gummy bears exit the oiler and are conveyed into an optical sorting system. High-resolution cameras scan each piece for size, shape, and surface defects. Bears that are deformed, broken, or discolored are identified by the vision system and removed by high-speed air nozzles. Approved pieces continue to the packaging line. Packaging is determined by product format: stand-up pouches, pillow bags, tubes, or bulk boxes. The cleaned gummy bears are weighed or counted using multi-head weighers that drop exact quantities into form-fill seal machines. These machines unwind printed plastic film, form it into bags, fill the bags with candy, and seal the top and bottom using heat-sealing jaws. Bag weights are controlled within +1 gram tolerance. Excess weight is trimmed in real time by the weigh-filler interface. Each package receives a date code, lot number, and barcode through an inkjet or laser coder. Vision systems verify the print quality, placement, and code accuracy. Improperly coded bags are automatically rejected. Finished bags are grouped by format and quantity and sent to secondary packaging. Secondary packaging uses automatic case erectors to form cardboard boxes. Robots or pneumatic arms load bags into the cases according to a stacking algorithm. Once filled, cases are sealed with hot melt glue or tape and printed with case-level traceability information. At the palletizing station, cases are stacked in predetermined patterns by robotic arms equipped with suction pads or mechanical grippers. Slip sheets are inserted to stabilize each layer. Full pallets are stretch-wrapped with tension-regulated plastic film and labeled with shipping data, including batch codes and destination tags. All stages of production are governed by programmable logic controllers. Each machine, from dissolver to depositor, oiler to packer, communicates with the central control system through industrial Ethernet. SCADA systems display real-time data, including syrup concentration, starch temperature, mold fill rate, curing status, polishing speed, and packaging counts. Environmental controls are maintained throughout. In the curing room, air handling systems monitor and adjust temperature and humidity minute by minute. In the packaging area, overpressure systems keep air clean and filtered. In mixing rooms, positive pressure and stainless steel surfaces ensure hygiene. Every equipment contact surface is food grade and cleaned using clean-in-place cycles or automated CIP skids. Hot detergent and sanitizing solution are circulated through tanks, pumps, and pipes on a scheduled cycle, verified by conductivity sensors and time logging. Ingredient traceability is enforced by barcode and RFID scanning at every stage. From glucose syrup intake to final packaging, every lot is digitally recorded and linked to each production batch. Quality control samples are pulled at each phase: post-mixing, post-curing, post-cleaning, and post-packaging, and tested for texture, color, pH, bricks, weight, and shelf life. Multi-flavor mixing is also supported. After curing, differently flavored gummy bears can be blended in programmable mixing drums. Servo-controlled gates release predetermined quantities of each variant, and slow tumbling ensures uniform distribution in every final package. Jolly Rancher hard candies are manufactured through a continuous high-temperature process that transforms raw materials into smooth, glossy, and intensely flavored glass-like confections. The production begins with the bulk handling of the base ingredients: granulated sugar, liquid glucose syrup, water, malic acid, flavor oils, colorants, and stabilizers. These ingredients are delivered in bulk. Sugar in silo-fed dry transfer systems, glucose syrup in heated stainless steel tanks, and flavoring compounds in sealed drums. Each ingredient is stored under controlled conditions and introduced to the production line via automated PLC-controlled dosing systems. The process starts in the dissolving station. Granulated sugar is conveyed from silos through screw feeders into a large capacity dissolving vessel. Simultaneously, liquid glucose syrup is pumped from its storage tank into the same vessel. Water is added to reach the appropriate liquid content. High torque agitators mix the ingredients as the vessel heats, typically reaching 110 degrees Celsius. The sugar fully dissolves in the syrup, forming a thick, translucent solution. The resulting sugar glucose solution is pumped into a high-efficiency vacuum cooker. This critical piece of equipment raises the temperature while lowering the pressure, allowing the mixture to be cooked to extremely high solids content without excessive caramelization. The syrup is boiled under vacuum to between 150 degrees Celsius and 160 degrees Celsius, reaching a final moisture content below 2%. The end product is a highly viscous, super concentrated candy mass nearing the hard crack stage on the sugar thermometer. Temperature and moisture levels are controlled by inline probes. As the candy mass reaches final cooking point, it exits the vacuum chamber under pressure and moves into a cooling and mixing table. This table is heated from below and cooled from above to bring the temperature of the mass down to approximately 120 degrees. Hot enough to remain pliable, but cool enough to allow incorporation of heat-sensitive ingredients. While the mass is still semi-fluid, malic acid, flavoring oils, and food-grade colorants are injected through precise metering pumps. These ingredients are introduced through static mixers built into the cooling table, ensuring even distribution. Each flavor variant, such as watermelon, green apple, cherry, blue raspberry, or grape, is handled in a dedicated mixing zone to prevent cross-contamination. The candy mass takes on its final color, aroma, and acidic intensity at this stage. After blending, the flavored candy mass is fed into a batch, former or continuous rope former. Inside this system, the mass is compressed and shaped into a thick rope using counter-rotating rollers. The rope is then pulled through a sizing system that gradually narrows and elongates it to a uniform diameter. Servo-controlled rollers and feedback sensors maintain consistent tension, ensuring that the candy rope holds steady dimensions along its length. As the rope advances, it enters a rotary forming die. This machine uses synchronized cavities on two rotating drums to cut and shape the candy rope into individual pieces. Each cavity matches the intended candy shape, a rectangular tablet with beveled edges in the case of Jolly Ranchers. As the rope is fed between the dies, individual pieces are sheared off and simultaneously molded into their final form. The forming process is extremely fast, with cycle rates exceeding several hundred pieces per minute per line. Formed candies fall directly onto a moving belt, which carries them through a cooling tunnel. The tunnel is divided into zones with gradually decreasing temperatures, typically from 25 degrees C to 10 degrees Cc. Chilled, filtered air circulates above and below the conveyor. This controlled cooling ensures that the candy sets uniformly without developing sugar bloom, cracks, or warping. The candy surface hardens into a glossy, non-sticky shell with a glass-like texture. After cooling, the candies are conveyed to the wrapping station. A high-speed flow wrapper aligns the pieces single file using vibrating rails and timing screws. Each candy is fed onto a roll of waxed or metallized film printed with branding and product details. As the candy moves forward, the film is folded around it and sealed longitudinally with a heated crimping wheel. The ends are simultaneously twisted or heat sealed, depending on wrap format. Wrapping speeds often exceed 1,000 candies per minute per line. A vision system checks each wrapped candy for seal integrity, print registration, and size conformity. Cameras detect misaligned seals, unwrapped pieces, or malformed shapes. These are automatically removed from the belt using pneumatic ejectors. Approved candies continue downstream to the bulk collection point. Wrapped candies are collected and conveyed into multi-head weighers or piece-counting systems for final packaging. For bagged formats, vertical form-fill seal machines form pouches from roll stock film, fill them with the target weight or count of candies, and seal them with heated jaws. The top and bottom seals are crimped, and a tier notch or zipper may be added depending on format. Inkjet coders print date codes and batch numbers on each bag. For assorted packs, mixing drums or belt combiners randomize candies from multiple flavor lines. Servo-controlled gates release each flavor in programmed ratios. Blending is continuous, monitored by optical sensors that track color distribution across a moving belt. After primary packaging, bags are grouped into cartons. Carton erectors form boxes from flat blanks, apply glue or tape, and receive packs via robotic pick-and-place systems. The boxes are sealed, date-coded, and labeled with product information. Each box is checked for completeness using weight sensors or barcode scanning. Cartons move to the palletizing station. Robotic arms stack cartons in interlocking patterns onto wooden or plastic pallets. Slip sheets are inserted automatically between layers to improve load stability. Once the pallet is complete, it is transferred to a stretch wrapping station. A rotating arm applies stretch film tightly around the stack. A label printer applicator places barcoded shipping labels on two adjacent pallet faces. Each major system, dissolvers, vacuum cookers, batch formers, rope sizers, rotary molders, cooling tunnels, wrappers, weighers, and case packers, is governed by programmable logic controllers. The PLC network is linked to a central SCADA system, which visualizes process parameters in real time. Operators monitor syrup concentration, cooking temperature, rope speed, forming pressure, wrapping rate, and line efficiency from control stations positioned throughout the plant. Ingredient traceability is built into the software. Every raw material lot is scanned upon arrival, stored in the ERP system, and assigned to a batch number. As the batch flows through cooking, forming, and wrapping, each step is logged automatically. Final products are traceable by barcode to their raw material sources and production parameters. Clean in-place systems run automatically at the end of each shift. The dissolvers, pumps, piping, and mixing tables are flushed with hot alkaline solution, followed by clean water rinses and sanitizing cycles. Cooling belts are brushed and vacuumed. Forming dies are disassembled, cleaned manually with food-grade solvents, and reinstalled using quick clamp mechanisms. The entire factory is divided into controlled zones: raw handling, cooking, forming, packaging, and palletizing. Positive air pressure is maintained in high hygiene areas. HEPA filtration systems remove particulates from circulating air. Ambient humidity and temperature are tightly regulated, as both influence candy texture and crystallization. Factory floors are sloped for drainage and sealed with epoxy for easy sanitation. Safety systems include temperature interlocks, overpressure valves, infrared burn detectors, and emergency shutoffs across all cooking and forming zones. Machines are equipped with safety guards and light curtains. Wrapping and cutting stations include trap guards and automatic stops when foreign objects are detected. High-volume candy factories operate multiple parallel lines to meet demand. Each line runs continuously, producing tens of thousands of Jolly Ranchers per hour. Combined output can exceed 1 million pieces per shift. Candy that fails inspection or is generated during startup and shutdown is collected in a reclamation bin and disposed of or recycled in non-retail applications under controlled conditions. Jolly Rancher production is a fusion of sugar chemistry, thermal control, servo-driven precision, and automated material handling. The transformation from dry sugar to glossy hard candy involves phase change, concentration, superheating, and rapid cooling, all while maintaining tight tolerance in size, shape, and texture. The candy's signature clarity and smoothness are the result of precise cooking and air-free handling. The bite resistance and slow dissolve are dictated by gelatin-free formulation, extremely low moisture, and uniform crystal inhibition. Color intensity, tartness, and flavor intensity are tightly tuned in, dosing systems calibrated to deliver fractions of a gram with every cycle. No part of the process is manual. From sugar loading to pallet stacking, each action is governed by machines, motion controllers, thermal sensors, and inline verification tools. Each Jolly Rancher is cut, formed, cooled, wrapped, inspected, and packed in exact synchrony with the line's conveyor rhythm. The process is repeatable, uninterrupted, and engineered for scale. Nerds candy production begins with granulated sugar as the core ingredient. Delivered in bulk via silo trucks, the sugar is stored in food-grade silos and transferred into the system through pneumatic conveying lines. The sugar crystals are metered using loss-in-weight feeders and introduced into the initial tumbling drum, the nucleus of the entire Nerds production process. The defining characteristic of Nerds is their irregular pebble shape and crunchy shell. This is achieved through a continuous layering process that transforms small sugar crystals into larger, asymmetrical, coated pieces. Production starts with microcrystalline sugar particles selected for their uniform size and dryness. These seed crystals are placed into a slow-rotating stainless steel coating drum. Inside, the environment is warm and dry, with dehumidified air pumped in to prevent clumping. As the drum rotates, a fine mist of sugar syrup is sprayed onto the tumbling seeds. The syrup is composed of dissolved sugar and glucose, kept at a precisely controlled temperature and viscosity. After each syrup spray, dry granulated sugar is dusted onto the seeds. The wet syrup binds the dry sugar, and centrifugal motion within the pan ensures even distribution around each particle. The syrup sugar drying cycle is repeated hundreds of times in quick succession, forming rough, uneven lumps that define the Nerd's shape. Drying occurs continuously using a stream of low humidity, temperature-controlled air directed through perforated panels under the rotating pan. The airflow evaporates moisture from the syrup, setting each new layer of sugar into a hardened outer shell. The mass increases by milligrams with each cycle. The longer a particle stays in the pan, the larger and more jagged it becomes. This tumbling and layering process continues for 45 to 60 minutes per batch. Throughout the process, real-time particle sizing is conducted using an inline imaging system. Cameras mounted above the pan capture live footage and analyze the average diameter and surface profile of the particles. Once the growing Nerds reach target size, they are automatically discharged through a slide gate at the base of the pan. The rough white sugar lumps exit into a vibratory conveyor that removes dust and separates underdeveloped pieces. Air jets blow away fines, while a mesh sieve sorts by size. Any particles below the acceptable size threshold are recycled into the seed stream for the next batch. The acceptable pieces move toward the coloring and flavoring stage. Flavoring begins with batch division. The uncolored nerds are split into flavor groups: grape, strawberry, watermelon, cherry, lemonade, and others. Each group enters a dedicated coating pan where they are flavored and dyed. These pans operate at higher rotation speeds to encourage rapid coverage. A fine mist of ethanol-based flavoring and food-safe dye is sprayed onto the tumbling pieces. The formulation includes fruit acids for tartness, aroma oils for intensity, and synthetic or natural dyes for color. The sprayed flavor and color mixture penetrates the porous surface of the sugar nugget, resulting in bright, vibrant colors and intense taste. As the solvent evaporates, the flavor becomes locked into the outer layer. Color intensity is monitored by spectrophotometers mounted above each pan. If deviation is detected, the spray nozzles adjust dye concentration in real time to maintain consistency. Once flavored and colored, the nerds are dried and cooled using forced ambient air blown over vibrating conveyor beds. These conveyors are lined with food-safe mesh belts to allow airflow from below. The drying stage ensures that the candies are free from any surface moisture or tackiness. Target surface temperature falls to around 20 Celsius to 25 degrees Celsius. The final coating step is polishing. Polished nerds exhibit a glossy, non-sticky exterior that resists clumping. Polishing pans, similar in structure to coating pans but lined with smooth, non-stick material, are used for this purpose. As the candy tumbles, a mixture of carnauba wax and food-grade glazing agents is sprayed in a fine mist. The pans rotate at medium speed, allowing the nerds to rub against each other and buff their outer surfaces. The process lasts around 10 to 15 minutes per batch. The polished candies pass through a second set of sifters and inspection belts. Optical sensors identify off-color pieces, misshapen forms, or oversized clusters. Air jets remove rejected items from the conveyor and send them to the waste stream. The remaining pieces are ready for blending and packaging. Nerds are sold in assortments, which means different flavors must be combined in accurate ratios. This is managed by a computerized batching and blending system. Each flavor is held in a vibratory feeder that releases product onto a shared conveyor belt in precise weight percentages. Real-time flow rate monitoring is conducted using load cells beneath each feeder. The combined stream of multiple flavors forms a randomized mix of colors and shapes that fills each package. Packaging is handled by vertical form-fill seal machines and custom filling stations depending on container type. For the iconic dual-chamber box, a specialized dispenser fills two parallel compartments simultaneously. Each compartment is connected to a dedicated flavor feeder, ensuring separated streams of two flavors into the same package. The box is folded from flat blanks using a rotary carton former, and hot melt glue is applied to the seams. A hinged paperboard flap is inserted as the opening mechanism. As the boxes move down the line, a laser coding system marks each with a production batch, date code, and serial trace number. A high-resolution vision system verifies the print quality and scans the surface for correct alignment and structural integrity. Any faulty boxes are removed by push-arm rejectors and sent to the quality hold station. For other formats, such as pouches, tubes, or novelty containers, nerds are portioned by either piece count or net weight using multi-head weighers. These machines use radial feeding trays and weigh buckets to measure out small portions with extreme accuracy. The weighed product is released into packaging film or preformed containers, sealed, and passed through metal detectors for safety compliance. Once packaged, the product is conveyed into case packers. Here, Robotic arms pick up individual units and place them into corrugated shipping boxes according to a preset stacking pattern. Case sealers apply hot glue or tape to close the cartons, which are then labeled and conveyed to the palletizer. Automated palletizers use robotic gantries to stack cases onto wooden or plastic pallets. Each layer is placed with millimeter accuracy to maximize vertical and horizontal stability. Slip sheets are inserted as needed to prevent shifting during transit. Once the full pallet is stacked, it moves to a stretch wrapping station. A rotating arm applies tension plastic film to secure the load. A printed label with shipping information, SKU, pallet number, and barcode is applied before the pallet is routed to the warehouse. Throughout the production line, programmable logic controllers manage all operations, from syrup spray timing to coating pan rotation, flavor dosing, weight checking, and packaging synchronization. A centralized SCADA system displays real-time data on batch progress, line speed, environmental conditions, and machine health. Operators can adjust parameters through touchscreen HMIs without stopping the line. Clean-in-place systems are used for syrup lines, coating pans, and mixing tanks. At shift's end or during changeovers, hot water and cleaning detergent are circulated through the spray nozzles, pipes, and pump systems. Coating pans are wiped down, and flavoring stations are flushed with ethanol to remove residues. Inspection cameras and flavor-specific tools are verified between batches to prevent cross-contamination. Air quality is maintained by HEPA filtration, especially in the syrup spray and flavor coating zones. Airlocks separate high-precision areas from packaging zones. Temperature and humidity are maintained to within +1 degree Celsius and +3% RH throughout the production floor. All surfaces are made of stainless steel or food-grade polymer, sloped for drainage and sanitized daily. Ingredient traceability is enforced from raw sugar intake to finished package output. Each micro batch of flavoring and coloring is tagged with barcodes and scanned into the production system. Every box of Nerds can be traced back to its sugar batch, flavor addition time, pan number, and packaging line. Every piece of Nerds candy is smaller than a pea, lighter than a raindrop, and made with such intense precision that over 1 billion of them can roll off a single line in just one day. And while they might look like random, rainbow-colored pebbles, each Nerd is actually a layered, engineered crystal. Hard, crunchy, tangy, and wildly addictive. But the process starts with something incredibly basic: a single grain of sugar. That tiny grain is the seed. It's what every Nerd grows from. In the factory, raw sugar crystals are sifted and sorted by size. Only those that fall into the ideal micro range, small, dry, perfectly angular, make it to the next stage. These seed crystals are loaded into massive stainless steel pans that look like oversized cement mixers, tilted on an angle and constantly rotating. This is where the real transformation begins: panning. Panning is the centuries-old candy-making technique used to build layer upon layer of sugar around a center. For Nerds, it's done at high speed and microscopic scale. While the drum spins, a fine mist of sugar syrup is sprayed inside. It lightly coats the tumbling seed crystals. Almost instantly, the moisture begins to evaporate, leaving behind a thin, glassy sugar shell, but that's just the first layer. Over the course of hours, this process repeats: syrup in, drying, syrup again. Hundreds of ultra-thin layers build up, hardening each time, until a grain of sugar the size of a salt crystal becomes a tiny, oblong candy with a satisfying crunch. The panning pans are kept in warm, low-humidity rooms to control drying speed. Too fast, and the layers crack. Too slow, and the candies clump. Operators monitor texture constantly, using gloved hands to feel for stickiness or roughness. They're not just letting the machine run, they're listening to the sound of the tumbling Nerds. That soft rattle? That means the coating is hardening just right. Once the Nerds have reached their target size, and yes, every flavor is slightly different, they're ready for their first big moment of color. In a separate set of rotating pans, the candy cores are sprayed with ultra-concentrated food dye and flavoring oils. Each batch gets its own color and taste. Strawberry red, grape purple, watermelon green, blue raspberry, lemonade yellow. The dyes are sprayed in fast pulses, then immediately sealed with a fine dusting of confectioner's glaze to lock in shine and prevent bleeding. If this step goes wrong, colors can mix or turn dull, so fans blow filtered air across the pans to speed drying without cooling the sugar, and operators constantly inspect samples under bright light. But here's the wild part, nerds aren't uniform. That bumpy, irregular shape? Totally intentional. During panning, the candies grow unevenly. Some clump slightly, some roll more than others. It creates that signature texture, each piece unique, but still the same size class. No molds, no presses, no cutting. And that matters, because the final blend, the colourful jumble inside each box, is carefully calculated. In the flavouring room, technicians pour separate batches of nerds into a multi-compartment blending carousel. Each section holds a different flavour and colour. Sensors track flow rate, weight, and count. When the carousel spins, it releases a precise ratio of colours into the packaging line. This is how every box ends up with that balanced mix. Never too much grape, never too little strawberry. Now comes the packaging phase, which moves faster than the eye can follow. Nerds boxes are made from pre-printed cardboard, folded and glued by high-speed cartoners. The boxes are tiny but precise. Each must hold just the right amount of candy without crushing it or leaving too much headspace. Volumetric fillers drop the nerds in, and a vibrating plate settles the candy for a perfect fit. Then the box flaps are heat sealed, encoded with batch numbers and expiration dates. For the dual flavor nerds, the ones with the classic split box, everything doubles. Two separate hoppers feed into either side of a center divider, and the box is engineered with a special tab that allows you to shake out one flavor at a time. That mechanism is tested for strength and fit using robotic arms that flex and squeeze every fifth box to make sure it opens cleanly and doesn't leak. And if you've ever bought a big Nerds rope, that's a whole different line. It starts with a string of gummy, a flexible gelatin-based rope made from corn syrup, sugar, and gelling agents. As the rope emerges from its extruder, it's still tacky. That's when thousands of nerds rain down from a curtain above, sticking to the sticky surface like gravel to tar. The rope passes under gentle rollers that press the nerds into place without squashing them. Then it's cooled, cut, and wrapped in crinkly plastic at up to 200 units per minute. The entire nerds operation is built on control. Temperature, airflow, and humidity are measured constantly. If the air is too humid, the sugar won't crystallize properly. If it's too dry, the candy can crack. Every machine is calibrated down to the millimeter. Even the rate at which syrup is sprayed is controlled by computer. Too much, and the candy melts into blobs. Too little, and it never grows. And behind the scenes, it's kept remarkably clean. Despite the sugar dust in the air and the thousands of pounds of dye in rotation, the facility is spotless. Operators wear full protective suits, face shields, and shoe covers. Equipment is scrubbed daily. Separate rooms handle allergens, and each flavor is kept in its own sealed system to prevent cross-contamination. The process may seem like chaos, bright colors, spinning drums, rattling boxes, but it's incredibly orchestrated. The noise alone is surreal. Each panning drum sounds like marbles in a dryer. Dozens spin at once, overlapping into a chorus of high-frequency clinks and low mechanical hums. There's the hiss of steam from the syrup tanks, the drone of conveyor belts, the soft hiss of powdered glaze being sprayed. It's the sound of billions of tiny candies coming to life. What makes Nerds different from other candies is how raw and elemental they are. There's no molded shape, no inner core of chocolate or nougat. They're just sugar grown into pebbles, flavored and polished. But that simplicity hides a shockingly delicate process. One batch of syrup off by a few degrees, It can throw off the entire panning schedule. A sticky drum, it clumps. Die flow too strong, it streaks. So operators constantly tweak, test, and taste. And yes, they taste nerds throughout the shift. Flavor uniformity is crucial. Each flavor must be bright, tart, and clean, with a crisp crunch followed by an acidic punch. Even slight deviations in acid levels, citric, malic, tartaric, can dull the flavor or make it harsh. So sensory panels evaluate every batch before it gets boxed. In the end, those tiny boxes you find at checkout counters, movie theaters, or Halloween baskets are filled with some of the most carefully grown pieces of candy on earth. No molds, no presses, just layers and layers of spun sugar, built over hours, hardened with air, colored by mist, and tumbled into the crunchy, chaotic rainbow that is nerds. Each roll of Smarties contains exactly 15 tablets, pastel discs that weigh less than a gram each, yet hold their shape so perfectly they can survive being dropped, shaken, or sat on without crumbling. They're smooth, chalky, lightly tarred, and almost impossibly consistent. And behind that simplicity lies a candy production process that's surprisingly loud, dusty, and engineered to run with near zero waste. Smarties have been made the same way since 1949, when Edward D., a candy maker from England, moved to New Jersey and converted old pellet-making machines, designed for pharmaceuticals, into candy presses. The process still relies on compression rather than cooking. No baking, no melting, no pans of hot sugar. Just dry ingredients, blended and compacted under tons of pressure to form a candy that's hard, smooth, and somehow melts on your tongue. Everything starts with the powder blend. The recipe includes dextrose, citric acid, calcium stearate, and natural or artificial flavorings. Dextrose is the main component. It's a fine, sweet sugar derived from corn that dissolves quickly and gives Smarties their rapid, melt-in-the-mouth texture. Citric acid is what provides the sharp, fruity tang in each flavor. Calcium stearate acts as a flow agent, keeping the powders from clumping or sticking to the equipment. The flavorings and colors are added in carefully measured amounts, each one blended separately depending on the final color of the tablet. Each flavor, orange, pineapple, cherry, strawberry, grape, is mixed in massive stainless steel blenders that can hold hundreds of pounds of dry ingredients at a time. The powders look like soft pastel flour, tinted gently with color: pink for cherry, yellow for pineapple, purple for grape. These mixes are sifted to remove any lumps or foreign particles, and then loaded into holding bins above the compression line. From there, gravity takes over. The powdered candy blend is funneled into the hoppers of rotary tablet presses, machines originally designed for pressing pills. Each press consists of a rotating table filled with die cavities and a set of punches, upper and lower, aligned above and below each die. As the table spins, the punches descend and compress the powder into hard, compact tablets. No heat is used. It's purely mechanical force, tens of thousands of pounds per square inch, pressing each candy into shape. These presses are fast. A single machine can produce thousands of Smarties per minute, each tablet formed in a fraction of a second. You can hear the click-thump rhythm of punches landing hundreds of times per minute, echoing through the factory floor. The speed and pressure must be perfectly calibrated. Too much force, and the tablets crack. Too little, and they crumble in the wrapper. As the tablets are formed, they're immediately ejected onto a conveyor belt and sent to inspection. They travel under high-speed cameras and laser counters that check for missing pieces, size irregularities, and color consistency. Broken or chipped tablets are blown off the belt with puffs of air and collected for reprocessing. Ground back into powder and reintroduced into the mixing stage. The flawless tablets continue down the line to wrapping. Smarties are famously packaged in tight rolls of 15, wrapped in clear, crinkly plastic with twisted ends. That roll is another engineering feat. To begin, the candies are grouped by a gating system, mechanical paddles that count out exactly 15 tablets per drop. These tablets slide into plastic film that's being unspooled from a massive roll, moving in perfect sync. A forming collar wraps the film around the candy stack, and heat-sealing jaws bond the film edge. Mechanical fingers twist both ends of the roll, like twisting a piece of taffy at speeds fast enough to blur. It all happens without stopping. The wrapping line moves continuously, synchronized to the tablet press output. If the press slows down, the wrapping slows. If a jam occurs, say a tablet gets stuck in the chute, a robotic sensor stops the whole line within milliseconds to prevent damage or miswraps. Each finished roll is shot into a collection bin where it joins thousands of others for boxing. Depending on the final destination, Smarties rolls are packaged into retail bags, bulk boxes, or specialty gift packs. High-speed cartners scoop up rolls by the dozens and drop them into pre-folded boxes. Every package is weighed, sealed, and labeled with batch information so it can be traced back through every step of the process. But the real complexity of Smarties lies in how clean and controlled the whole system has to be. The powder used to form the tablets is extremely fine. Think baby powder consistency. Left unchecked, it can coat machines, gum up sensors, and create safety hazards. So Smarties factories use powerful vacuum systems that run continuously, pulling excess dust from the air and cycling it through filtration. Workers wear coveralls, gloves, and hairnets, and their shoes go through cleaning stations at every doorway. Even the air itself is managed. Humidity is a constant enemy in tablet candy production. If the air is too moist, the powders clump and stick. If it's too dry, static electricity builds up, which can cause inconsistent fills or attract dust to equipment. Climate control systems run year-round, keeping the production floor within a very narrow range of temperature and humidity. Every major ingredient bin is sealed and vented. The room is positively pressurized so that outside air can't drift in. And then there's flavor. Even though each Smartie is tiny, the flavor has to be concentrated and consistent. That means flavoring oils and acids must be measured down to fractions of a percent. The blending process is carefully timed. Too short, and the flavors don't distribute evenly. Too long, and the powders heat up from friction, which can cause off notes in the final candy. Each batch is taste tested during production, with sample tablets pulled from the press and dissolved in water to measure acid levels and flavor balance. And every flavor gets its own dedicated line or cleaning cycle. Because Smarties are so small, it only takes a few stray tablets to contaminate the color or taste of another batch. Between flavors, the tablet presses are completely disassembled, dies and punches removed, hoppers cleaned, dust vacuums run, and sensors wiped down. The turnaround is fast, but thorough. It's part of what lets Smarties keep their signature clarity in both flavor and color. Quality control doesn't stop with production. Once rolls are packaged, random samples are pulled from each batch and subjected to stress tests. Boxes are dropped, crushed, and shaken to simulate shipping conditions. Rolls are unwrapped and counted to confirm the exact number of tablets. Tablets are measured for diameter, weight, and break strength. And in one test, machines apply pressure from above to see how much force it takes to snap a Smartie. If it breaks too easily, the press calibration is adjusted. And yet, for all this precision, there's almost no waste. Smarties is a closed-loop operation. Any chipped tablets are recycled into powder. Any overfilled rolls are rewrapped. Even rejected wrappers and cardboard from the packaging floor are collected, shredded, and sent to recycling. The factory hums with quiet efficiency. Nearly everything that enters the system leaves as a sellable product. The result is a candy that hasn't really changed in decades, not because it couldn't, but because it doesn't need to. The pastel colors, the slight tartness, the crinkly wrapper, it all adds up to something nostalgic, efficient, and deeply engineered. And what makes Smarties different from other candies is how much is done without cooking. There's no molten sugar, no caramelization, no frying or tempering. It's all compression and control. The candy press is the heart of the process, a machine originally built for medicine, reimagined for sweetness. It doesn't just make Smarties fast, it makes them identical every single time. Jolly Ranchers are some of the hardest candies on earth. Literally. They're engineered to resist biting, built to last, and packed with so much concentrated flavor that a single piece can keep your mouth watering for 10 minutes straight. But behind each brightly colored lozenge is a high-temperature, high-speed process that turns molten sugar into razor-sharp glass with a fruit flavor punch. From raw ingredients to individually wrapped pieces, making a Jolly Rancher is a mix of thermodynamics, timing, and some very sticky science. It starts with just 3 main ingredients: corn syrup, sugar, and flavoring. Sounds simple, but the balance between those first 2 is critical. Sugar gives Jolly Ranchers their sweetness and structure. Corn syrup prevents crystallization and keeps the final product smooth and transparent. Too much sugar and the candy becomes grainy. Too much corn syrup and it won't harden properly. These 2 syrups are pumped into massive stainless steel mixing tanks, each one big enough to hold hundreds of gallons. Here, the sugar and corn syrup are blended together into a thick, pale slurry. Industrial agitators keep the mix moving constantly to prevent any settling or clumping. Once blended, the mixture is heated to over 300 degrees Fahrenheit in a continuous cooker, a machine that looks like a long metal tube wrapped in insulated coils. This step is where everything starts to change. As the temperature climbs, water begins to boil off rapidly. The mixture thickens, darkens slightly, and takes on a glossy sheen. Steam rises from the cooker vents, carrying with it the warm, sweet smell of caramelizing sugar. But unlike caramel, which cooks lower and browns more, Jolly Ranchers are heated just high enough to reach the hard crack stage, between 300 and 310 degrees Fahrenheit, without burning. At this point, the sugar solution becomes incredibly viscous, almost like hot lava. This is candy glass, brittle, shiny, and ready to snap once cooled. The key here is moisture removal. To get the signature glass-like hardness, the mixture must be almost completely dry, less than 2% moisture. That's why the heat is so high and why it's applied so precisely. Even a 1% change in moisture content can mean the difference between a rock-solid candy and a chewy, sticky mess. Vacuum cookers are often used in later stages to finish the dehydration process without overheating the syrup. Once the syrup hits the right consistency, it's ready for flavoring and coloring. But here's the trick. It's still blazing hot. Too hot for delicate flavor compounds to survive. So the liquid is transferred to a cooling table or chilled mixing drum, where it's gently agitated and allowed to cool just enough, usually down to around 275 degrees Fahrenheit, before the flavor oils and food coloring are added. This is where things get intensely aromatic. Cherry, watermelon, green apple, grape, and blue raspberry, the iconic Jolly Rancher lineup, all rely on custom flavor blends that are surprisingly concentrated. Just a few drops per batch are enough to infuse thousands of pieces. As the oils hit the warm candy, they vaporize slightly, creating a wall of scent. Workers in this area often wear filtered masks, not because the vapors are dangerous, but because the smell is so overwhelming it can linger for hours. After flavoring, the mixture is ready to be formed, but it's still thick and sticky, like honey that's been left in the sun. At this stage, it's called the rope. The candy mass is loaded into a pulling machine, where it's kneaded and stretched in long glossy strands. Pulling introduces tiny air bubbles and gives the candy a smoother texture and slightly lighter color. But for Jolly Ranchers, this step is minimal. They're meant to be clear and dense, not fluffy like taffy. So the pulling is short and precise. Next, the rope is fed into a forming machine. A set of calibrated rollers and dies that shape the candy into the familiar oblong lozenges. The rope passes through the rollers, which press it into molds spaced at exact intervals. Each cavity forms a single piece, cutting and shaping at the same time. The machine must keep pace with the candy's cooling curve. Too slow and the candy hardens before it's molded. Too fast and it deforms or sticks. Timing here is everything. The forming rollers run in perfect sync with the pulling speed, adjusting automatically to changes in viscosity. If the candy cools too much, the rope is reheated slightly by overhead lamps or heat plates to keep it pliable. If it's too hot, fans kick on to speed the cooling. Every second matters. Jolly Rancher syrup can go from soft to rock hard in under 10 seconds if left alone. Once formed, the individual candies ride a conveyor through a cooling tunnel. This tunnel is about 40 feet long and packed with chilled, filtered air. The candies must be cooled evenly and gradually to avoid developing internal stress, which can cause cracks or fractures later. As they travel, they harden into solid, glossy lozenges with a smooth surface and near-perfect transparency. Now comes the wrapping, arguably the most technical step of the entire process. Each Jolly Rancher is wrapped individually in a special double-layer film, waxed inner paper and a colourful printed outer film. This wrapping isn't just for branding, it's engineered to withstand extreme stickiness. Even at room temperature, Jolly Ranchers are hygroscopic. They absorb moisture from the air, which can make them tacky. The wax coating on the inner wrapper prevents the candy from fusing to the packaging, while the outer layer protects it from humidity, heat, and light. To apply the wrapper, high-speed flow wrappers align the candies with rotating belts and cutting jaws. The film is cut to size, curled around each piece, and sealed with a heated crimper that twists the ends. These machines can wrap hundreds of candies per minute. So fast, the wrapped pieces look like a blur as they shoot off the end of the line into bins. At this point, the candies are cool, hard, and shelf stable, but not yet ready to ship. They're sent through a final inspection system that uses cameras and weight sensors to catch malformed pieces, missing wrappers, or empty wrappers accidentally sealed with no candy inside. Faulty units are kicked off the line with air jets and sent to a reclaim station where wrappers are stripped and the candy is remelted. The good batches move on to packaging. Depending on the final format, Jolly Ranchers are dropped into bags, jars, or boxes. For fun-size packs, robotic arms count out a set number of wrapped candies, funnel them into plastic pouches, and seal the tops. For bulk jars, conveyors load hundreds of candies into plastic tubs, which are then lidded and shrink-wrapped. Every unit is batch-coded, dated, and weighed, and all of this happens under a strict quality protocol. If a single bag in a batch fails a weight or seal check, the entire batch is flagged for inspection. Behind the scenes, data flows constantly. Sensors track temperature at every stage, from syrup cooking to cooling tunnel exit. Viscosity is monitored in real time. Belt speeds, humidity levels, room temperature, and even air particle counts are logged. Operators monitor it all from control stations with touchscreen dashboards, ready to tweak parameters at a moment's notice. And the environment must be spotless. Sugar dust is a serious hazard in industrial settings. It's flammable, sticky, and a magnet for bacteria. So the production floor is kept under positive pressure, filtered continuously, and cleaned at the end of every shift. All machines are made with smooth, food-grade steel and designed to disassemble quickly for daily sanitation. What's perhaps most fascinating is how scalable the process is. The same basic steps: cook, flavor, form, cool, wrap, apply whether a facility is making 10,000 pieces an hour or 10 million. Everything is modular. Need to make more watermelon? Operators adjust the flavor tanks and swap in a red dye cartridge. Need to make heart shapes for Valentine's Day? Change the mold plates on the forming rollers and recalibrate the wrapping alignment. And because Jolly Ranchers are made from a solid sugar glass base, they have an almost indefinite shelf life. up to 18 months with no preservatives. That makes them ideal for long shipping routes, hot climates, and bulk packaging. It's also why they're so popular as party favors, parade tossers, vending machine fillers, and Halloween staples. But at the core of every piece is that glassy crunch, that hard, smooth texture that doesn't yield until the very end. It's not just candy, it's carefully crafted sugar architecture. The entire process is designed to preserve that structure, from the moisture level in the cooker, to the cooling curve on the conveyor, to the twist in the wrapper.